All right, so I think we'll get started. For people in the audience, we're also streaming online, so we will also be taking questions from the online community as well, and try and have it as interactive for the online community as we have it for you guys here as well. And I'm checking my playback, so I'm hearing that on the side. All right, so. Yeah. So as I say, we're streaming live on YouTube and with scripts. So I'm going to give just a quick, brief overview of what's actually happening. But just quickly, for those of you who are online, you may not be 100% sure of where you're actually watching us today. So we're in San Diego, California, and this is our wonderful ocean view with the Torrey Pines golf course. Very, very brief overview, and all of the people that you'll be hearing from today will be speaking much, much more in depth about each part of this. But this is kind of overall of what we will be speaking about. So at the beginning, we'll be talking about samples, how to prepare your samples, different type of LCMS profiling techniques that you can use, a little bit about some of the data processing, mostly on more of this identification, because this is where we spend the majority of our time, not only just in the lab, but in the field in general, of course. We spend a lot of our time looking at identification, and a lot of the talks you'll hear about today are on trying to help you out on identifying your metabolites, faster ways to do that, and tricks and tips in making it faster. And then at the end of the day, we'll talk about quantification, and Bill will do a very nice talk on that. So the people that you'll be hearing from today are going to be Elizabeth, who will be talking about sample preparation, how to make sure that you're going to get the right type of molecules that you want to see. This is always kind of the first step that you need to be thinking about when you do any sort of metabolomics. What type of sample do I have in front of me? Because of course you can extract for lipids or you can extract for other type of molecules, and so this is going to be the first decision that you're going to have to make to try and decide upon what type of area of the metabolome that you're going to be looking at. And then Bill's going to be speaking both about our open access lab here at Scripps, how you can use that, how you can get into get into that lab and start doing some of these experiments for yourself. And also later on in the day about the quantitation aspect, how to really nail down exactly the compound that you're looking at and make sure that it's as super sensitive as it possibly can be. Amelia is going to be speaking about different types of instruments that you can use, why those instruments may be more useful for one type of experiment over another type of experiment. Xavier is going to be speaking about various different annotation techniques. This is not only just picking up what type of adducts have been made in your experiment, but also how you're going to try and get quickly to some sort of understanding of what compound classes, and maybe if you're really lucky, what actual compound you're looking at. Both Rafa and Carlos are going to be speaking about identification in two different ways. Rafa is going to be speaking about using MSMS data, fragmentation data, to be able to identify your compounds. And Carlos is going to be talking about identification using some really cool techniques using stable isotopes. And so this is our overall plan for the day. As I say, I'm going to just give this intro, and then I'll be quiet for the rest of the day and pass it on to these very knowing and wonderful individuals. And as I say, then we'll go on to Elizabeth. So without further ado, I'm going to pass it over to her.
So my name is Elizabeth Billings, and I'm a technician here at the Mass Spec Metabolomics Core. And today I'll be talking a little bit about mass spec sample preparation and some techniques you can use to effectively prepare your metabolomic samples. So just a little bit of overview of what a typical metabolomics workflow looks like. So the very first step is deciding what kind of samples you're going to be selecting for your experiment. So this decision can be made for a lot of different reasons. It could be what's convenient. It could be the model organism you're using. There's a lot of different factors that go in. But at the end of the day, you need to decide whether you're going to be using a biofluid, a cell culture sample, or a tissue sample. And each one of those is going to have a little bit of a different preparation procedure. And the first step after you decide which samples you're going to extract is going to be quenching metabolism. So as soon as you extract your samples, whether it's cells, tissue, or biofluids, the metabolism is constantly going to be changing. So it's very important to either snap freeze or heat fix your metabolites, and I'll talk a little bit more about which one of those is more favorable. Lastly, after you've extracted your samples and you've quenched metabolism, important storage is important. It's important to properly store your samples. So as I said, metabolism will continue to change, so if samples are improperly stored, they could degrade and your results will be not as good. So after you've properly properly quenched your metabolism, you're going to extract your metabolites from your sample, and then you're going to also conduct some sample normalization. So especially if you're looking for fold changes between two groups, it's important to normalize your samples because if you have different amounts of metabolites in each sample, your results are going to be very skewed. So that will be the part of the workflow I'll be discussing. My colleagues later on will be discussing data acquisition and data processing. So like I said, there's a few different types of samples you can use. So for biofluid samples such as urine, cerebral spinal fluid, blood, plasma, etc., you're going to need between 20 and 100 microliters per sample. This will give you more than enough metabolites to work with, enough for normalization. It's a good amount. For cell cultures, it can vary by cell type. So smaller cells, you'll need more. For example, T cells, you'll need more like 1 million cells, whereas larger cells, you'll need less. So a good average we typically recommend is at least 1 × 10⁶ cells. And for metabolites extraction, you can use either an adherent or non-adherent cell line. For tissues, you need at least 10 milligrams of fresh weight, and this can also vary based on your tissue. For example, some tissues are a lot harder to break down, such as eye tissue, so you may need more depending on what kind of sample you're working with. So like I said, one of the first steps in metabolite extraction after quenching metabolism is removing any contaminants. So every biological sample you're going to extract is going to have proteins and particulates. And these can interfere very immensely with your signal when you're trying to do a metabolomic analysis. So if there's still protein in your sample, that signal will drown out anything of interest. So it's important to remove those proteins during your sample prep. Also, like I said, quenching metabolism is very important. So there's a few different approaches to quenching metabolism and metabolite extraction. The first two on the right, solvent and temperature, are two that we recommend pretty universally, whereas pH and molecular weight cutoff are techniques that are also used but have some limitations. So solvents are very good for extracting and precipitating out proteins. Using the correct solvent can allow you to remove any protein from your sample as well as extract your metabolites from your tissue or biofluid. So you can use polar or non-polar solvents depending on your application, and this will allow you to extract your molecules. Additionally, temperature is very helpful for quenching metabolism. So like I said before, you can either use extreme cold or extreme heat. The one issue with extreme heat is that it can damage your metabolites. So that degradation that we talked about, that can happen if you use heat. So we recommend using cold, such as a liquid nitrogen bath or dry ethanol ice bath, when preparing your samples and also as soon as you extract them to quench the metabolism. The other benefit of cold is it's very quick. As soon as you put your samples in that extreme cold temperature and they reach it, your metabolism will be quenched. As I said, pH is another method that you can use for fast inactivation of metabolism, but not all metabolites are stable in different pH conditions. So if you're doing some kind of target analysis where you specifically want to look at acid-stable compounds like nucleotides, this could be a method you choose. But if you're trying to do an untargeted analysis, if you use an extreme pH to quench metabolism, you're going to end up removing a lot of your metabolites of interest. Additionally, molecular weight cutoff is another method, but it's not as effective or efficient as using solvents or temperatures. So it could be good if you've prepared a sample, you precipitate out your protein, and you're still seeing protein signal. You could use something like molecular weight cutoff to try to remove more protein in larger molecules. So also now that you've quenched your metabolism, you've started to extract metabolites, we're going to propose a method that you can use to extract both your hydrophobic and your hydrophilic metabolites. So as we know, metabolites are very diverse chemically. There's a lot of different kind of compounds found that are metabolites, and not every single one will be absorbed with every single method. So it's important when preparing your samples and also when preparing your method to be able to view as many of these as possible. So I'm going to go through a few procedures that you can use for sample preparation. First, I'm going to start with a non-mechanical method. So this would be something that you would use for liquid samples or for cell culture samples. So if you have samples from cell cultures, you want to lyse the cell and release the metabolites, and then you want to use solvent to extract them. So, like I said, if you start with between 5 and 10 million cells and ice cold water, we recommend a solvent solution of ice cold water to acetonitrile to methanol, 1 to 2 to 2. Now, every lab has their different recipe. You have different ways to do it. Some may be more suitable for different cell types, but this is just a general recommendation. So the first step you're going to do is you're going to vortex your samples. You're going to then immediately freeze them. In this case, we had a bath of liquid nitrogen, and then you're going to thaw them. So what this is going to do is it's going to start to break open your cells and quench that metabolism. You then want to sonicate your samples again to kind of break everything up, mix it together, get those metabolites out, and you're going to repeat that step again. So you're going to vortex, freeze, and thaw. So this cycle of freezing and thawing will get out as many metabolites as possible. Then, in order to precipitate out the proteins effectively, we recommend storing your samples in -20 degrees, either overnight or for an hour. The longer it's stored for, the more protein can be extracted out. But for some samples, after an hour, all the protein is precipitated out. So after you've precipitated out the protein, you're going to go ahead and transfer your samples to centrifuge tubes, spin them down, take out that solvent because what's remaining is the protein pellet, and then you want to use that solvent and you're going to evaporate it, and then again resuspend it in the solvent you're going to use for your procedures. So if you're planning on doing an LCMS run, you want to put it in a solvent that's suitable for LCMS, and then you can sonicate again, extract, resuppernate it, and your sample's ready. So for cell cultures, there's a little bit of tips specifically for adherent versus non-adherent cell lines. So if you're using an adherent cell line, it's very frequent that you may use trypsin to remove your cells. So you want to avoid using trypsin in large amounts because it can interfere later down in your metabolomic analysis. So trypsin will show up as a peak, and that's not necessarily something you want. So if you're preparing your samples and you've already normalized some other way and you don't need to measure your protein amounts, you simply can wash the cells, scrape them into a vial, and prepare the samples without having to worry about measuring your proteins. What you want to do is you want to extract the same weight per sample and you want to reconstitute in the same volume. This will allow you to normalize your samples without measuring the amount of protein. If you are going to do protein measurement, again, you'll start with washing your cells with PBS. You'll quench your metabolism, put your cells into a vial, carry out those steps I discussed, and then you're going to save the proteins that were spun down in those pellets for quantification later. Some other specifics for biofluid sample prep. With plasma, urine, and cerebral spinal fluid, you may use a different amount of solvent than you were using with cells. And again, what you're basically doing with these, since you don't need to lyse the cells, is you're vortexing, sonicating, breaking up your metabolites into your solution. So the other type of method you can use for sample prep is a mechanical method. So this is used for solid samples such as organs, tissue species, and requires the use of a homogenizer. So as I go through these steps, you'll notice they're pretty similar to the cell extractions, but with this extra step. So you'll start again with 10 milligrams of wet tissue. You'll add a solvent, in this case 1 to 4 ice cold water to methanol. And then you're also going to need some sort of homogenization beads. So this will be important because you're working with a solid tissue. You need to break it down, get those metabolites out. So the first step after you've prepared is to put in the homogenizer. And then once your whole sample is broken down, you're going to sonicate and store overnight, again, to precipitate any proteins that you don't want in your sample. Once you remove it, you're going to transfer it to centrifuge, remove the solvent that's in there, replace it with the solvent you're going to be using for LCMS, sonicate, and then you're going to remove that solvent because that's now your sample, and you're going to save the protein in case you need it for quantification, or if you're not using it, just so like I said, normalization is very important when doing a metabolomics experiment. So for different types of samples, there's different strategies. So for tissues, you may use weight, or you may do some sort of protein quantification to make sure that you know how much protein is your sample, and you can use that to scale your results. For cells, you can use either cell number, or you can do some sort of protein or DNA concentration. A lot of people will do both. They'll document what the cell number is, and they'll also document the protein concentration. For biofluids, volume is good for most biofluids, but it's not very good for urine. So as we know, urine will dilute and change depending on how much water somebody has drank. And so it's a little more challenging to normalize urine. So that's something to be careful if you're using that as your biofluid for your sample. So like I said, quality sample prep is going to create higher quality results. So for your samples, you always want to reduce background ions. So anything you use in your sample prep or even during your cell culture could show up later on. So it's good, especially if you're working with proteins, to reduce the amount of salts, buffers, and surfactants, as those can show up as very strong peaks when you're doing your results. Polyethylene glycol, PEG, which is a universal polymer, is frequently in solvents. So if you have a lower grade solvent, you could have PEG contamination, and PEG ionizes very well and will suppress the signal that you're looking for. Solvents such as DMSO may also interfere, but are usually okay in smaller amounts. Again, the same thing's happening there. DMSO is going to ionize a lot better than your sample, so it could suppress your signal. Again, polymers and plasticizers, we recommend avoiding, if you can, when you're doing your preparations, autoclaved plastics, because it can make the plastic leach into your sample. Additionally, it's important to reduce biological contamination. So this is especially important when you're working with proteomics samples. So keratin, which is found in human skin, hair, nails, if it gets into your proteomics sample, you're going to have a lot of signals from the keratin and not as much from your protein. Additionally, cross-contamination between samples can affect your results, so make sure when you're preparing your samples, just good scientific procedure, don't use the same pipette to pipe multiple samples. Also remember that you need to remove all your cellular media. So again, it'll have a lot of background ions. There's a lot of nutrients in there that you don't want interfering with your results. Additionally, like I said, sample degradation is a big issue. So you want to make sure that you've properly stored your samples. If they're stored at room temperature, they're going to start to degrade. Now, shifting gears a little bit, you've prepared your samples, you're looking at certain biomolecules, you want to know what methods are you going to use. So for different biomolecules, they're going to ionize different ways. So depending on the type of compound, there's going to be different ionization mechanisms. So something like a peptide would protonate or deprotonate and could be viewed in positive or negative mode, but something like a protein we know is only going to show protonation and is going to be best viewed in positive mode. So I'm sure you can all read this, but basically do a little bit of research before you're looking at your sample, because, for example, if you ran a protein negative mode, you wouldn't see any results and you'd be like, what happened? So it's good to do your research on your specific compound. Additionally, some of these, even if they do ionize, for example, oligonucleotides are sometimes a little tricky, so it may take a few steps, a few tries to get it to ionize via your specific method. So some methods that you can use when you're looking at biomolecules that we offer in the core is what I do every day, is ESI. So ESI can be used in positive or negative mode. It has a good range. It's very accurate, so you can use it for less than 5 ppm error on small biomolecules. And you can also use it for proteins, because ESI allows compounds to be multiply charged. So even if you have a large protein, say BSA, you will see multiple charges in a range below 3,000 daltons, and you'll be able to use those and use a software to deconvolute those results to determine what the mass of your protein is. So like I said, ESI TOFs have very good sensitivity and accuracy, and they also are paired well with XCMS, which is, like I said, with those sample prep procedures, it's very easy to prepare samples for LC. The one thing to watch out for, like I was saying, is ESI has a lower salt tolerance. So if you have salts in your samples, especially if you're doing a direct injection, those are going to show up. If you hook up a column and do some chromatography beforehand, salt's less of an issue because you can wash it out before your sample is injected. Another method that you can use for looking at samples, which is especially good if you have a very small volume of your sample, is MALDI. So MALDI can be used to look at a variety of compounds, including proteins, peptides, carbohydrates, etc. And the nice thing about MALDI is there's different matrices you can try. So For example, something like synapinic acid is very ideal for proteins, but if you have a smaller molecule, you may use something different. So MALDI has a very high mass range. I've observed proteins up to 250,000 Daltons. But the one thing is, as you get higher mass, your resolution's decreasing, so you're going to have a lot wider peak. So MALDI is very good if you need a quick verification. It's very easy to automate, but it's not going to give you as accurate and as precise of a mass as something like ESI. MALDI does have some tolerance of salts. When you spot a sample, you're going to spot on your sample, spot on your matrix, let it dry, and then there could be surface salts that can be easily removed with water. So this is a technique also that is good for mixtures because you're making a spot. You point the laser at different areas of your spot and give different signals. ESI is less suitable for mixtures, especially if you're doing a direct injection, because all your compounds are going to be showing up at the same time and overlapping. The one thing, though, to watch out for with MALDI is, like I said, you're using a matrix compound, which is usually some type of acid. So if your compound that you're studying is not very stable, it could degrade in the acid and break up. This isn't something we see typically because most of the compounds we study are pretty acid stable. But also, if you're looking at peaks below 700, you could have matrix interference because the matrix peaks are going to be in that range. Another method that we use and recommend for compounds that are less than 500 Daltons and easily vaporize is GCMS. So GCMS is really good for compounds like naphthalene that are stable in volatile solvents. They easily vaporize. The nice thing is there's a NIST database of GCMS data which you can compare to. So if you run your sample through a GC, you can directly compare it to this database. It's really good for target analysis, so if you know what you're looking for, you can get a good max out and match it. It's also historically been used for rapid disease diagnosis, but it does have thermal mass limitations. Like I said, the compound needs to be easily vaporized, so if it's only stable in water, you can't run it with GCMS. Also, you can only look at compounds up to 500 Daltons. Another method that we use in lab is ion trap. So ion trap is really good for proteomics work. So for proteomics work, we're going to take a complete protein, digest it down using trypsin digestion, and we're going to run MSMS. So what we can do with that is we can go in and identify your protein as well as post-translational modifications. And again, with this method, you can go ahead and compare it to a database. So our technician, Lynn, who runs this, she uses the NCBI database search. So she can go in and match the expected peptides and get the sequence information. The one limit with ion traps is the 1/3 rule. So you can't observe fragments that are less than 1/3 the mass of your precursor. So that is my last slide. If there are any questions, please let me know.
Thank you very much, Elizabeth. Yeah, there's a lot of people online who are asking, and for those of you in the audience as well, all of the slides, all of the material that you see here today will be available on YouTube directly after. So if there's something you want to go back to and listen to again, just go to the XCMS Online Institute page and you'll see it there. Trying to think of other questions that we had online. For those of you who are online, just write into the chat window. I know it's moving pretty quickly on there. It's quite nice. We have about 250 people online who are watching across the world at the moment. Is there any questions from the audience before we move on? Okay. Bill, I'm going to hand over then to Bill, who's going to be speaking about open access.
Paul? I'm Bill Webb. I've been here at Scripps for about 18 years. 16 of those years, I've been overseeing the Open Access Lab. The Open Access Lab is an MS facility that is open for anyone at Scripps to come and use if they want. And also it's open to folks outside of Scripps to come and use if they want. We have 4 LCMS systems available for all of you. 3 of those are going to be adjunct single quad instruments. One of them is an adjunct LC top MS system. All 4 of these are plumbed into an adjunct 1260
Yeah, it should be
Pointer?
on the end if you press the green button.
Ah, here we are. Okay. So we have, we have all four are plumbed into a 1260 LCMS system, which is coupled with a DAD detector, which allows you to observe absorbances over a wide range of wavelengths. So if you're running experiments in your lab, you see a peak absorbing a certain wavelength, you'd like to get some mass data on that peak, you can then type in that wavelength into this instrument and then duplicate your experiments down in the open access lab and get some mass data on that unknown peak. We supply some C4 and C8 columns for you all to use. C4 are for the large molecule folks, the guys looking at BSA compounds and higher. C8 columns are nice because they cover a very wide range of compounds, from the low mass to the medium high mass, about 35 kD. You're also capable of using your own. Not every compound you want to look for is going to retain well in C4 or C8. And if you're looking at like carbohydrates or Krebs cycle compounds or these really small hydrophilic things that don't retain well, we can set up helic methods, which Amelia and other folks will talk about a little later on. But we can take this sort of customizable work and get the open access lab set up for you so you can be looking at these types of compounds. And when you do sit down with me and we do get trained, what we do is we'll build you guys a method that's unique to you. So when you go to run your samples, you'll load this method. You can run your samples, and if your project changes, you can make changes in this method. So if you're looking for a different mass range of compounds, you can change your mass range. If you're bringing on a different column and you want to use a different gradient, then you can change your gradient. You're going to have a method that'll be unique to you and your project when you come and sit down. So quads versus TOFs. Why would you pick one over the other? The TOFs have much better resolution, and therefore they have much better mass accuracy. You look at this photo on the one on the right, it's the same compound. On the one on the right, you see here's your C12, and here's your C13 isotope. This is run on a quad. The one on the left is run a TOF. Here's your C12, and here's your C13. And you've got miles of room between these two isotopes. This type of resolution allows you to achieve really high mass accuracy. That's 5 ppm. And in mass spec lingo, when you say 5 ppm mass accuracy, what we're saying is that if you have a compound that's 1,000 Daltons, you can measure it to within 0.005 Daltons. If you want to publish data, many publications require MS data with this 5 ppm mass accuracy. The TOF instrument in the open access lab does this all the time. So another benefit of having really high resolution is the ability to pick up very small modifications on large proteins. Quads tend to have mass accuracies of about 0.1 to 0.01%. So if you have a rather small modification on a large protein, that mass may not be able to be resolved by a quad instrument. TOF instrument, because of the better resolution, can pick up these smaller changes on larger proteins. So why use a quad then? Well, quads are very robust, right? Quads are also less expensive instruments to purchase, so they're less expensive to use. If you don't need the high-res data, unit mass measurement is fine. Quads are super instruments. Quads are also really good at quantifying compounds. They have a scan method called selected ion monitoring. Right here, SIM. SIM means you set your scan range, so you're only looking for 1 Dalton. Now, most folks, when they come down and use the instrument, they'll set the scan range a few hundred above, a few hundred below everything they want to see in the sample. But if you are interested in a certain compound and a serum extract, but if you only care about one thing, but there's thousands of compounds present, then you can use the SIM setting only scan for that one M over Z value. And it's really useful if you want to quantify how much that you have in your sample. So some of the considerations we have with the open access facility is that it's a shared resource. Everybody uses it. So we're kind of only as good as our worst user. And I think of the old IT adage, garbage in, garbage out. You come down with a really concentrated, complex sample, and you inject it on the column. It's going to pretty much make everyone's day a little worse off. So you want to make your sample reasonably clean. It doesn't have to be totally purified, but the cleaner it is, the better off that you're going to be, the better data that you'll get. Sensitivity. So these instruments are all very, very sensitive. Every morning we run check standard on them at 80 femtomole per microliter, and we'll inject 1 microliter. That's 80 femtomole on column, and this is a peak that you get. Signal noise at 22.5. I mean, this is wonderfully sensitive. Of course, not every single compound is going to ionize as well. You're probably not going to be getting nanomolar sensitivity in everything that you analyze. But if you stay into like the 10 micromolar range, you're probably fine. Right? You'll have enough to get a nice clean signal, good data, dilute enough such that the next user comes and uses the instrument, they don't see your compound left over on the column. So the moral of the story is dilute, dilute, dilute. Anyone who's ever sat down with me has always heard me say the same thing. Dilute your samples. You may think it's dilute, it probably isn't that enough. Okay? So there's a setting you have when you go to set up your run where you can adjust your injection volume. It's quite common with synthetic chemists. They don't really know exactly how much they have. They're not sure what yields are, and these are totally understandable. So if you come down with a sample, you're not clear on how much you have, shoot less. Shoot like 1 microliter. If you don't see anything, that's fine. Go ahead and shoot 10. But rather go that route than shooting too much, seeing a very large overload on the column. You make good ions and walk away all nice and happy, but the next person comes up and they're going to see their compound, and they're going to see your compound in their sample. That's a situation we kind of want to avoid. We want to keep the instruments as clean as possible so everyone can get the best data they can. All right? That's pretty much it for the Open Access Lab. If you have any questions, feel free to send me an email. And if you have any questions now, I'll be happy to answer them.
Yes, there's one question from the online community.
Mm-hmm.
They're wondering if quads are more sensitive than tops, and if so, why so?
The sensitivity is pretty much equal. The only way you make it more sensitivity in a quad is if you use the selected ion monitoring scan mode. Quads scan a given range, tops scan a constant range all the time. Quads scan a given range. The larger the range you scan, the more time it takes to do that scan, the less sensitive you are. If you go to selected ion monitoring, that is the narrowest scan range you have. It's 1 Dalton. You can accumulate far, far more scans in a period of time using that mode than you can do a full range scan. So the answer to the question is they're both very, very sensitive. You may be able to tweak it more on the quad end if you go for the selected ion monitoring mode.
All right. Thank you very much, Bill.
You're welcome. Thanks, Paul. Yeah.
All right. For our next speaker, we're going to have Amelia, who's going to be speaking about untargeted LCMS instrumentation.
Paul, we got one more question.
Oh, yes.
For Bill. They asked, is a Q-trap a good instrument for global metabolite analysis?
It's nice because you get MS and MS data, which is really helpful in your global metabolomic analysis. I don't think a Q-trap gives you the high resolution data that you really need to identify your unknowns. And because it's a trapping instrument, as Elizabeth pointed out in her talk, you're sort of limited by the 1/3 rule. If you trap a bunch of similarly charged compounds in a given space, the similar charges are going to have repulsive effects in all the compounds present in that trap. And the upshot is everything about 1/3 the mass of the parent ion you don't really see. So the 1/3 rule is kind of a drawback with common traps, and the fact that they only use unit mass is kind of a drawback. But it's nice they offer MS data, which is really useful if you want to make an ID. All right.
Good morning, everybody, and thank you, Paul, for this introduction. So my presentation is about untargeted liquid chromatography and mass spectrometric approaches for the profiling of the metabolite. This presentation is divided in 2 parts. The first part is about the chromatographic methods. The second part is about the detection by mass spectrometry. So from this moment on, when I talk about untargeted detection, I mean full scan acquisition measurement of the M over Z, the mass over charge value for the metabolites ionized in the mass spectrometer. So let's start with the chromatography. The chromatography separates the molecules, in our case the metabolites, in our sample. This separation is based on the interaction of the molecules with a stationary phase and a moving phase, which in turn depends on the physical-chemical properties, this meaning the chemical structure of the metabolite. Here we have a column as it appears in our laboratories, and if we zoom in this part, we can see that it is packed with spheric particles. These particles usually have a core of silica, which is derivatized with the stationary phase, which is actually interacting with the molecules. Here in this example, you can see a reverse phase particle derivatized with the alkyl structure, CH.
Amelia, sorry to interrupt, but
Yes.
can you speak a little louder for those?
Yes, sure. So this is just an example. We have we can choose among a variety of different chromatographies, and when we analyze complex matrices, as for example urine, we can use a guard column, also called a pre-column, which basically prevents the contamination of the analytical column, and is positioned right before the main column, as here. As you can see, it's shorter, and usually it contains the same type of stationary phase as the analytical column. So compounds, metabolites with high affinity for the stationary phase will elute later compared to compounds with low affinity for the stationary phase. What we detect at the end is a chromatogram reported here for a targeted analysis of 6 metabolites, which reports the abundance of the metabolite compared to the retention time, irrespective of the retention time. As you can see here, for untargeted metabolomics, we obtain usually chromatograms which are way more complex, and the reason is because we normally detect starting from 3,000 metabolites on. So often these metabolites can coelute from the column, so we can see these basically peaks, which are a result of the overall ion current detected for the metabolites. Of course, this is a total ion chromatogram. So, but why using chromatography? If this basically is introducing an additional time dimension in our analysis. So we have an answer here, but I'm curious from our audience if you have any idea about this. Why do we actually use chromatography? This is complicating our analysis. Any input? Okay, so the first reason, perhaps the most important one, is because we want to reduce ion suppression. In order to understand this point, we can just imagine to directly inject the sample as it is without separation in the mass spec. The first event in the mass spec is the ionization of the metabolites. But in our sample, we can have metabolites at high abundance and easy to be ionized, and other which are at, of course, low abundance and perhaps more hard to be ionized. So the first class will suppress the ionization of the second class, and therefore that will affect the sensitivity. If we perform a separation before, we will substantially decrease this effect, therefore increasing sensitivity and increasing the number of detected future metabolites. As we can see here, so one of the ionization sources often used is the electrospray ionization. As we can see here, the ion of the matrix, which might be in excess compared to low abundance analytes, can ionize easier compared to the analytes, and therefore suppressing the ionization of the metabolites. The second aspect is that the mass spectrometer cannot discriminate isobaric compounds. So compounds with the same m/z value, with the same molecular weight, cannot be discriminated only by mass spectrometry. For this reason, if we introduce here we have the example of testosterone glucuronide and iptestosterone glucuronide, which have the same m/z value, so therefore the mass spec sees them together as a sum of intensities. But if we add an additional chromatographic separation, we can discriminate them and we can identify them. Moreover, as we say, the retention time depends on the physicochemical properties of the molecule. This meaning that we can use the order of elution and the information about the retention time to support the identification of the metabolite. Last, since this increases the sensitivity, it allows us to obtain fragmentation spectra at higher quality. There are several parameters that affect our chromatographic separation. So the first class is the parameters that affect the mobile phase composition. So the mobile phase is usually composed of two solutions. One is in water and one is in organic solvent. And these solutions are enriched with salts. The first reason is because we need to control the pH, but also we need to control the ionic strength of our mobile phase. We can mix these solutions in different percentages according to a gradient, a chromatographic gradient. Here we have some example. As you can see, the composition of the mobile phase both depends on the type of stationary phase, but it also depends on the ionization polarity that we use in our experiments. And of course, it depends also on the nature of the metabolites and the analytes that we want to detect. When the composition of the mobile phase is kept constant over time, we are performing an isochromatic separation. When we change it over time, we are performing an elution, so-called in gradient. So the other factor is temperature. What we tend to prefer in the laboratory is working at room temperature. This, of course, because simplifies all the analysis. But there are some occasions in which this is not the best condition. For example, for the analysis of lipids, which are highly retained inside the column, we usually prefer to increase the temperature of the separation. Why? Because this increases the elution, and it also increases the flow rate through the column. However, we have to be careful with this because it can affect the high temperature, can affect the stability of some classes of metabolites. So we always need to know in which classes are we interested in order to be sure that we don't detect artifacts derived from the thermal degradation of metabolites. The last factor, perhaps the most important, is the type of stationary phase. How do we choose the column, the stationary phase? So in here we have two main points to make our decision. The first is the time factor. Do we need high throughput, or let's say we have a small cohort of samples, or we are working with more than 500 samples, for example. The other factor is what is the class of metabolites that we are mostly interested in. Are they polar or are they unpolar? So basically, are we interested in lipids or central carbon metabolites, and so on. For the first question, we usually have two options. One is high performance and the other one is ultra performance liquid chromatography. The main difference is in the diameter of the particles packed inside the column. As you can see here, ultra performance liquid chromatography is using particles with smaller diameters in the order of 2 micrometers. This comes with several advantages. First, the resolution of the chromatographic peaks is better, is improved, and this comes also with a greater sensitivity. However, we need to couple this chromatography with mass spectrometers which have adequate scan speed. But overall, the big advantage of using UPLC over HPLC is the time factor. That is basically that we can perform the separation in shorter gradients. The alternative is the HPLC approach with bigger particles. So there is less likelihood of clogging the column. We can interface this separation also with mass spectrometers that have a lower scan speed. The point is that the separation will be slower, and the resolution, of course, will be not at the level of a UPLC system. This comes also with a big difference in the price of the column. So, of course, in this case, in order to choose which column is the most adequate for our study, it depends on the number of samples that we need to analyze, if we need high throughput or not. Do we always need chromatography? Is this necessary? Is anybody working in his laboratory without chromatography? Okay. The answer is we prefer to use chromatography because we have the additional information for metabolite identification. But there are some cases in which we can, for the design of the experiment, we cannot use chromatography. For example, real-time metabolome analysis. In this case, we already have a time dimension, and we cannot include an additional time dimension, which is dictated by chromatography. The other situation in which we cannot use chromatography is when we have a very high throughput study. This means more than 500 samples. In this case, it's more convenient performing flow injection analysis. However, we still have to consider that these things have cost of sensitivity, and we will lose information about the identity of the metabolites. We cannot use the retention time to support the annotation, and also we cannot perform MS fragmentation experiments by isolating the precursor in a specific retention time window. Okay, so how about the type of metabolites that we want to measure? How do they affect the choice of the stationary phase? In this case, we have two types of columns that we normally use for untargeted metabolomics. The first type is reverse phase chromatography. In reverse phase chromatography, we have the silica particles, which are derivatized with apolar chains as a C18 or C18. The interactions are mostly hydrophobic interactions with nonpolar metabolites. This meaning that we can separate the nonpolar metabolites like lipids. The grouping starts from a high percentage of water, and then it goes up to high percentage of organic solvent, and going back and re-equilibrating to the high percentage of water. Does anybody have an idea why do we perform this separation in graded, changing the composition of the mobile phase, or can just try to answer it? No, so the point is, yeah, partially. So basically, the point is that in untargeted metabolomics, we have a broad range of molecules that we are trying to separate. This meaning that some of them elute very fast because they don't have that much retention. The column doesn't have that much retention for these metabolites. However, some of them are very thick inside the column. And for this reason, if we change the composition of the mobile phase over time, we change the affinity of the analytes during the run for the mobile phase in respect of the stationary phase. And for example, if we increase the affinity for the organic component, we can start to basically release the interaction with the stationary phase, and basically clean up at the end of the run all the metabolites that are very stick to the column. So this is so far the type of chromatography that is broadly used in metabolomics. However, there is a problem with it because, as you can see here, the polar metabolites coelute and are not retained. So they are here at the beginning in the void volume. But when we talk about polar metabolites, we are talking about central carbon metabolites, and we are talking about amino acids. So this information for us is very important, usually in biology and in our experiments. So we need another technique, another way to separate them. To accomplish this, we can use a hydrophilic interaction with chromatography. So the difference in hydrophilic interaction chromatography is in that the stationary phase is derivatized with polar groups. These polar groups establish hydrogen bondings and ionic interactions with the analytes, and therefore are able to retain them and separate them. The mobile phase starts from highly organic with a small percentage of water and salt, and then goes up to high percentage of water and salt. Why this? This is because at the beginning of the run, we create a partitioning equilibrium, a liquid extraction system between the organic part of the mobile phase and the thin layer of water, which is mostly at the interface with the stationary phase and the polar groups. In this way, the polar analytes first partition mostly in the water layer, and at that point they are very close and they can interact easily with the polar groups at the interface of the stationary. there are several options for functionalizing this stationary phase, as you can see here. It's getting increasingly popular. However, it does not separate the hydrophobic compounds. Therefore, it's somehow complementary to reverse phase. It requires long equilibration times, and the column lifetime is shorter. This is because it can undergo side reactions with metabolites in our sample mix. And it comes with high cost. Here we have an example of helix separation of central carbon metabolites and amino acids. As you can see here, over a gradient of 35 minutes with an HPLC column, it's possible to separate the majority of them. And in this study, an important concept was demonstrated, which basically tells us that when we have limited amount of sample and we have limited time for analyzing these samples, the broadest coverage on biologically relevant metabolites can be achieved by performing helix separation with the negative electrospray ionization for mass spectrometry and reverse phase separation together with positive electrospray ionization mass spectrometry, as you can see here from the data. However, we have to point out that in the helix separation in positive electrospray ionization, we can still detect important compounds, for example, amino acids, which ionize well in that polarity. So as a take-home message, we have to consider, in order to perform an effective separation, we have to consider the type of stationary phase, the mobile phase composition, and the time factor. But how about the mass spectrometric detection? So why do we use mass spectrometry and we don't use NMR, nuclear magnetic resonance? So several laboratories use NMR. It is very good for quantification of metabolites. However, the sensitivity is not comparable with mass spectrometry. The other option is performing gas chromatography coupled with mass spectrometry. Again, several laboratories use this approach. It's very effective for some classes of metabolites. However, for others, it's less effective, and in particular for those that are not stable at high temperatures. This because gas chromatography is usually performed at very high temperature, in the order of 200 Celsius. While liquid chromatography provides good sensitivity and wide metabolome coverage, so it's usually the method of choice. So the detection happens in the mass spectrometer, which has mainly three components: the ionization source, the mass analyzer, and the detector. In Untargeted Metabolomics, we can choose among different ionization sources. However, the most used ones are the electrospray ionization source and the atmospheric pressure chemical ionization source. The first one was developed by John Fenn, who won the Nobel Prize for this development. So perhaps it's important to stressing out that the development of this technology impacted a really broad range of research field, and also, let's say, our daily life, because this is the technique that is mostly used in the analytical laboratories all around the world nowadays. How it works? So we have a capillary which is charged and basically is channeling the flow directly coming from the LC system to the mass spec. We have a potential here in the capillary, and then we have an opposite potential at the inlet of the mass spec. By electrospray, the solvent with the analytes is forming spray drops, and in this process, the solvent gradually evaporates. What happens is that the charges in these drops start to repulse each other, and as long as in the process of evaporating the solvent, they repulse even more, until the moment that the drop becomes very small and the charges explode. This is one mechanism. The other mechanism is that the ions are ejected once at a time while this tension increases. As a result, we obtain the ionized molecules which are channeled through this potential inside the mass spec. Nowadays, the configuration of this source is called the off-axis configuration, which is basically the basic difference is in turning the capillary of 90 degrees. Why this configuration is the preferred one? This is because in this way, only the charged species are channeled inside the mass spec, while the solvent and the uncharged species go directly to the waste. Therefore, this increases sensitivity and by reducing the effect of the matrix and the uncharged species. We can perform the ionization with its source both in positive and negative mode, and it provides us with the molecular ions together with several types of adducts depending on the mobile phase that we use. So this is the most used source in metabolomics. It provides us molecular ions and also multi-charged ions. It's a soft ionization, this meaning that there is very limited in-source fragmentation, and this is important for the identification of metabolites. However, we have ion suppression, and we have to consider that the ionization depends on the pK of the metabolite, but also on the composition, the pH, and the ionic strength of the mobile phase. Usually, we work with flows in the order of microflows. However, there is the option to decrease the flow to the nano range. This can be accomplished by using smaller needles and positioning them closer to the inlet of the mass spectrometer. The main advantage is that we increase sensitivity while decreasing the volume necessary for the analysis. As you can see here in this example, where they use a nanoprobe in order to directly sample the cytoplasm from a single cell. Then they through nanoflow, they directly channel this into the mass spec, and they obtain real time, they call it live single cell analysis of the metabolomic changes in the cell. The other option is the atmospheric pressure chemical ionization. This is also a soft ionization technique. The main difference is in the mechanism of ionization. So, first we have a nebulizer gas which flows in the capillary, and we have high temperature which is enhancing the vaporization of the sample. In this way, in this region, we obtain the nebulizer gas, which is usually nitrogen, and our nebulizer sample. For the coronal discharge, the nebulizer gas gets ionized, and in turn ionizes the solvent, which then, by in a chemical reaction, ionizes the analyte. It is usually beneficial for the analysis of low to medium polarity compounds, and these compounds should be easy to be vaporized because of the vaporizing step in the dissolution. It's considered generally complementary to ESI. It performs both positive and negative ionization. However, again, here we can have thermal degradation of the metabolites, so this aspect should be considered. So once that we obtain the ionized metabolites, then we have to separate them based on the mass over charge ratio. And this is accomplished by the mass analyzer. Two parameters are important in the selection of the mass analyzer in untargeted metabolomics. The first one is the mass accuracy. So the mass accuracy informs us on the error on the measurement of the M over Z value. Basically, what it tells us is how close is the measured value to the real value. So this is a measure of accuracy. In order to understand why this is important in untargeted metabolomics, let's give a look at this plot. It reports the number of metabolite hits obtained by matching an M over Z value against a metabolite database, for example, methylene, in function of the accuracy of error. So here we have high accuracy, here we have very low accuracy. As you can see, if we have low accuracy, we have a huge number of possible metabolites to consider for their annotation and identification of the molecule. While as long as the accuracy increases, this number decreases. Of course, the best results are obtained by coupling the putative annotation with the fragmentation experiment, as you can see here from But in general, we can consider that we can perform untargeted metabolomics with instruments that have at least 10 ppm of accuracy or lower values in ppm. In this respect, it is very important to calibrate the instrument, both with internal and external calibration. Internal calibration usually performs better. How about the resolution? The resolution is, on the other hand, informing us on the ability of the analyzer to discriminate between very similar M/Z values. Let's understand this with a real example. So we have the isotopic pattern here for Maui, measured at a resolution of 1000. While this is the isotopic pattern measured at a resolution of 10,000. So let's go back and forth again. So the advantage is here. We can basically discriminate masses which are very close to each other because this is and this is exactly the reason why we cannot use for untargeted metabolomics these analyzers, which, as Bill said before, are very good in terms of sensitivity and targeted quantification of the metabolite. But we rather use, we can choose among these two analyzers, the time of flight analyzer and the Orbitrap analyzer. The big difference is that the Orbitrap usually has higher resolution and better accuracy, but it comes with a cost which is higher. So in general, the time of flight analyzer is the first instrument in new laboratories, and the Orbitrap is usually applied in all those cases when the chromatography cannot be applied or in laboratories which have big resources. For example, having high accuracy is very important in flow injection analysis or real-time measurements. The top of the standards in terms of accuracy and resolution is still the Fourier transform ion cyclotron resonance instrument. As you can see here, in this case, we go in the range of ultra-high resolution and ultra-high accuracy. However, this instrument is very expensive. It is rarely used in metabolomics laboratories. So now that we know how to select the components of our workflow and set up the platform, we need to understand how to write down the analytical sequence, how to organize it. So this is an example for one of the studies that we are performing now in the laboratory. So we usually start with blanks. The reason is easy. It's just because at the beginning we need to know that our column is, the chromatographic column is not contaminated. So we need blanks, we check that the blanks are clean, and then we go ahead performing the quality control for the platform. This is accomplished by analyzing a standard solution of known metabolites at known concentrations, both at the very beginning and at the very end of the sequence. At this point, we start analyzing usually from 3 to 5 quality controls for the specific study. This meaning pooled samples from the cohort of samples that we include in our analysis. Why? So first, we need a reference for all the metabolites, all the metabolite features that we detect over the sequence in terms of quality control. On the other hand, this provides us a way to condition the column with the real matrix of the study since the very beginning of the analysis. At this point, we can start injecting the samples from the study and alternating to these samples, we inject the quality controls. At the end of the sequence, we can include an analysis of dilution series of the pooled sample. This because provides us information about the reliability of the semi-quantitative measurements for the metabolites that we detect in the study, as well as an automated fragmentation experiment which will aid us and speed up in the identification of the structure of the most abundant metabolites. At this point, we have collected our untargeted data, and we need to perform the data processing step, which involves peak picking, retention time correction, and chromatogram alignment, putative annotation, and data pretreatment for as a sample normalization or dealing with missing values. At that point, we have our big matrix of data, and we can perform statistical analysis to identify the dysregulated metabolites. At that point, we perform metabolite identification through the fragmentation experiments, but also the use of poor standards, and eventually data interpretation, both in the context of the metabolic pathway, but also at system level. And with this, I've finished, and I would be very happy to answer your questions. Thank you.
So, Amelia, we have a couple of questions from the online system. So, just before we do that, a couple of people were asking online why you're putting in the acid into your system.
In the mobile phase,
yeah,
you mean?
Thank you.
Okay. So that's the reason. Why do we put acid? So first, we have to ask ourselves, how do we detect the metabolites that we are interested in? Are we detecting them as positive ions? So this meaning protonated ions. If this is the case, acid aids in the formation of the protonated ions. So this is mostly the reason why we do that, because we can modulate the ionization, we can create the optimal conditions for ionization directly by directly tuning the mobile phase composition.
And sorry, just one last question. Some people were asking, I have to remind myself now, where was it? Yeah, the QC sample. So why do you think that we should be using QC samples in our run?
Okay, there are several reasons why it's very important to use them. So the first one is that technical problems can happen in the system, and we need to have a reference point to make sure of the reliability of our measurements, because we don't have internal standards in Untargeted metabolomics. So for this reason, it's extremely important to inject and analyze over the sequence these quality controls, because they have the same composition, they contain the same metabolite as our study samples, and they are injected periodically over the sequence. So they should, in theory, give always the same response, analytical response. So basically, they allow us to perform qualitative analysis.
Yeah.
Sorry, can you repeat the question? Yeah, so do you mean splitting the flow, right? Yeah, it's also, this technique is also called splitting the flow. So basically, yes, for sure, because this is the same. This connects to the advantage that we showed before by using microflows or nanoflows. So basically, if we direct part of the flow, as you suggest, to the waste, we decrease the flow to the mass spec, and this usually increases the sensitivity. So yes, for sure, this can be a good practice.
And it,
Could you go back to the sequence slide? So just to clarify, you're running your sample set, and beyond that is now your mid-sample to check your ground point. For the next step, you're rerunning the same samples.
No. No, they are different samples. So let's say that you have 20 samples in your study. You first condition the column equilibrated by running, let's say, 3 quality controls of pooled sample. Then you start with the first 5 samples in your study. You usually don't inject them in the order of the study, but you randomize the sequence in order to get rid of technical variation and technical drift over the sequence. After the first 5 samples, you analyze another quality control, and then you go ahead with other 5 samples, which are of course different from the previous ones, until you finish or you analyze all the samples that you have in your study. Yes.
Elizabeth, you said there was a question from online that you wanted to ask.
Yeah, I believe we covered a little bit. A lot of people are just asking about this use of a QC sample and how you would use that to normalize your samples afterwards, and how what
Okay, so we generally don't use it for normalizing. You do that only in the case that you you observe very significant drift in the signal over the sequence. So in general, what you do after the sequence is first opening all the quality controls and checking that the variation is in the order, is confined in the percentage that you can accept for your study. For example, you can expect a 30% of metabolite intensity variation. So taking the same peaks, you can estimate that. At that point, you know that the measurements in your sequence are readable. So you can go ahead with the analysis of the samples. If you figure out that this is not the case, that you have a variation higher than the error limit that you are willing to accept, in that case, you can. There are several options. For example, you can use the drift in the quality controls in order to correct the signal in the study samples. However, of course, this is not an ideal situation for the analysis.
All right. So with that, I think we should have some snacks outside. I believe Brian's probably already out there. So I'm going to. Thank you.
Thank you.
Yep. So for the online people, we'll be back in probably give us 20 minutes. And for everyone here, let's be back in, so 20 minutes, so 5 past. Good.
No, I'm trying.
Thank you.
I don't know how to turn on those lights.
Okay.
Yeah, I think these are all it's the only other lights you can put on are right in front of the screen. That way.
It's not bad.
Yeah, so I really with Amelia's questions.
All right, so we'll get started again. I hope everyone had a good break, both here and online. I'm going to pass it over to Xavier now, who's going to be talking about annotation in your data and how to try and get yourself onto looking at different parts of the identification process. So, Xavier?
Thank you. Thank you, Paul. So, as Paul said, I'm going to talk about data annotation. I'm going to first give an overview on LCMS data, and then I'm going to go through all the annotation strategies that currently exist for MS1 LCMS data annotation. So let's briefly go through the untargeted analysis workflow. We have our biological samples, then we analyze those with LCMS, we upload the raw data into XCMS online, and we have a feature list. We obtain a feature list. So we call a feature a peak or a set of peaks with a unique M/Z ratio and a unique retention time across all the samples. So the same peak in one sample. So all the peaks, across the different samples, the same peak. That's what we call a feature, right? A peak with I repeat, a single M/Z ratio, a unique M/Z ratio, and a unique retention time. Now, we want to annotate this feature list. Why do we want to annotate this feature list? Because LCMS data is highly dimensional and redundant, right? Let's imagine that we analyze just a single analyte with LCMS, and we observe what are the peaks, the M/Z ratio. This in the x-axis. This is the M/Z ratio, and this is what we're going to observe in the same retention time for that specific metabolite. We're going to see, if we use a positive mode, we're going to see probably the protonated peak, one or more adducts, probably some dimers, the isotopes, and as a result of in-source fragmentation, we are going to see in-source fragments and common losses as well, right? So per one single metabolite, per one single analyte, we're going to observe multiple peaks that all stem from the same metabolite. So there is a high dimensionality because we observe lots of peaks per metabolite, and there is a redundancy because, as I say, one metabolite, multiple peaks. Now that's a problem, right? Because this is those are two real examples, two real metabolites, pure standards analyzed with LCMS. We observe that there are multiple peaks. Some of them may be noise, but some of them maybe not. Some of them may be small, low-intensity adducts that are present here, and they are still there are valuable features that we can use to annotate the rest of the features. So we have multiple thousand of features in our LCMS experiments, and this is a problem because we cannot answer the question how many compounds are we profiling typically in LCMS experiments, because there is a problem trying to know what are the features that stem from the same metabolite, right? So this is why we want to use annotation, because we want to be able to know what are the features that stem from the same metabolite, and from all these features that belong to the same metabolite, which one do we want to grab and send to the QTOF, send to the mass spectrometer for MS fragmentation, so we can compare the fragmentation pattern with reference fragmentation patterns from available public libraries. And this is a perfect example to show that there are two types of cases where we can apply annotation. The first is annotation of MS1 data. This is what I've been talking before. We want to know what are the features that stem from the same metabolite, and then assign each feature with their, if it's an adduct, if it's a common loss, if it's an in-source fragment, an isotope. And then once we know that and we can fragment the corresponding feature, the one that we are more interested in observing, we can annotate. We're going to fragment this feature, as I said, and we can compare with available MSMS information. Now, if we don't find any match, then we can apply some annotation techniques for MS2 data. So we can then start to figure out what all these fragments may come from. Is this fragment correspond to a substructure of this metabolite? So we can start figuring out what, or at least narrow down the list of putative metabolites that this MSMS spectra can be, So we can purchase the standard and then analyze it to confirm this putative identification. So I'm gonna mainly talk about the first case, how to use the different strategies that we have to annotate MS1 data. And then I'm gonna cover briefly some computational strategies on how to annotate MS2 data, very, very briefly, because Rafa and Carlos, they're gonna explain how to do this annotation more from the analytical side, right? So there, we classified the existing annotation strategies into 5. First is the MS1 pseudospectral extraction. Second is using ad hoc mass rules to annotate. The use of biochemical knowledge. The use and integration of tandem MS data. And finally, use also retention time to annotate. So the first, as I said before, we need to know, it's very interesting to know what are the features that stem from the same and each metabolite, right? In this example, we have some features that elute at the same retention time, and they correspond to 2 compounds. So the idea is here that we have a computational strategy that is capable of grouping the features that stem from each metabolite, right? The blue features correspond to one metabolite. The orange features correspond to another metabolite. So with this, we can extract what we call the pseudospectra, which is formed by all the features that, again, stem from each metabolite. Now, there are 2 different techniques to computationally perform that. The first one is to compare the peak shape of these features. If the peak shape of 2 features are very correlated, are strongly correlated, then we can assume that those 2 features stem from the same metabolite. If they do not correlate, then we assume that they do not stem from the same metabolite. This is one of the core principles of one of the most widely used packages for data annotation in Untargeted Metabolomics, the package camera. And it does that. It starts comparing all the features, all the peak shapes for all the features to see if they correlate well enough. And it starts constructing a network to pull out exactly that, the groups of features that correlate well via the peak shape comparison. Now, of course, these sometimes some features may allude together, and they may correspond to 2 compounds. So it's difficult to know just by comparing the peak shape if some features stem from the same metabolite or not. So there is a more robust alternative to that, which is the use of peak abundance correlation. This is another technique. To explain how it works, let's show this example. Let's say that we have 4 features. Those are 4 features. This is in the x-axis, we have the M/Z ratio. 2 features, A and C, the blue ones, correspond to one metabolite. 2 other features, B and D, correspond to another metabolite. And we'll have these features, we're going to observe these features across all the samples that we have. Of course, the intensities are going to change. They're going to vary among samples. But the ratio between the features that stem from the same metabolite is going to be the same. So the ratio between A and C is going to be stable across all the samples. In other words, if we compare the area of A versus C and the area of B versus D, we're going to observe a linear relation. We are going to observe a correlation. So we can make use of that phenomena to extract what are the features that stem from the same metabolite. And if we compare areas of features that do not belong to the same metabolite, ideally or theoretically, we're going to observe a weak correlation. So by making use of that assumption, so by making use of that fact, we can group features based on if they belong or not to the same metabolite. So when we have extracted the MS1 pseudospectra, then we can start computing M/Z ratio distances between all the features that stem from the same metabolite, and we can compare those distances with those of known ad hocs. And with that, we can assign each feature with an ad hoc. We can assign it with an isotope, with proteinated species, and even common losses. And it's important to do that just after that we extract the MS1 pseudospectra, because it's less likely that we're going to find false relationships between unrelated features that appear at the same, that elute at the same retention time. In other words, if we start we start measuring all the different mass differences between all the features that elute at one given retention time, it's very likely that we're going to find spurious relationships, distances of 22, distances of 15, that correspond to a loss of water, or sodium, and it's easier to start getting false annotations. So if we do that right before the MS1 pseudospectra, if we first narrow down the list of features that we're going to start comparing distances among, it's easier to get more robust, or at least less false annotations. And this is very well discussed in this paper, where they actually talk about adding more relationships, not just the typical adducts or the common losses, but trying to add more complex relationships in order to get a more comprehensive annotation of the data. And they discuss also this phenomena as well, that if we take into account a lot of relationships, the more false positives we are going to probably observe. Let's move to another annotation strategy, the use of biochemical knowledge. There are some different strategies to do that, to use the biochemical knowledge to get better annotations. One very interesting to me is the projection onto pathways. This is actually implemented in the XCMS online system, and it aims at getting more robust putative identifications based only on accurate mass. So it assumes one hypothesis, which is the following. If a list of putative identifications are true, these should reflect a biological activity and thus show an enrichment on local pathway regions. Let's explain this with an example. Let's say that we have a feature list and that we have 10,000 features. We're going to search all these features by accurate mass search into a library, and we're going to obtain a list of putative metabolite identities. Now let's go through one per one. Let's go through all the features, these regulated features in our feature list. Let's start by this one, this feature here. This feature here could be attributed to different metabolites. Let's say that we assume that this feature here is this metabolite. Okay, we grab this metabolite and we project it into its pathway, and we observe. We also take a look at the metabolites that are close to this compound, and we see that there are no dysregulated features that by accurate mass could be attributed to any of the compounds that are close to our metabolite. So this makes no sense, or at least does not make a lot of sense from the biochemical perspective, from the biological perspective, right? Let's now assume that it's valine, that this feature here could be valine. And we grab valine and we project it into the pathway, into its pathway. And now we see that there are other features, dysregulated features, that could be attributed by accurate mass search to other metabolites that are in the same pathway and close to our metabolite. That makes more sense, right? It makes sense that if there is one feature, if there is one compound dysregulated in a pathway, other compounds in the same pathway are also be found dysregulated. So now with this we can assume that yes, this feature is in fact valine, and that the other features that are dysregulated are also those that we are observing here. Now let's move to another annotation strategy, the use and integration of tandem MS data, which is pretty interesting because it shows how we can use MS2 data to annotate MS1 data. How so? This by the use of in-source fragmentation. We have in-source fragments also in ESI, although it's a soft fragmentation technique. Some of the molecules are going to break in the source, and we're going to observe some in-source fragments. In fact, common losses are also as a result of in-source fragmentation, because the bond with the water is broken, so we observe the loss of the water here. And if we So these in-source fragments that we observe in MS1 data can also be observed in MS-MS low energy spectra. So if we, for example, take a look at a 0 or 10 volts MS-MS spectra of a certain molecule, those fragments that we're going to observe there are also the ones that we observe in a typical MS1 profiling experiment. So we can do that. We can compare the MS1 pseudospectra that we get with the MS-MS spectra, the low energy, I repeat, low energy MS-MS spectra or MS2 spectra of that molecule. And we're going to see a match. Probably the intensities are going to vary, the relative intensities, but the fragments should be there. And how often in-source fragment happens? This is a very interesting question, in my opinion. And we quantified this. What we did is we get all mailing. We went through all mailing, and we considered that those peaks that show at 0 volts, we consider those peaks to be potential in-source fragments. So we saw that we got this figure. We saw the percentage here in the y-axis. We see the percentage of metabolites, and in the x-axis we see that what's the percentage of metabolites that have 0, 1, 2, 3, 4, so on, up to 15 or more number of fragments. So we see here that more than 90% of the molecules in mailing in that time, that was in January, had more than one or more in-source fragments. So in-source fragmentation is a very common phenomenon. We see lots of in-source fragments. And this actually is being implemented in XCMS Online. We're gonna annotate also in-source fragments with this approach. So now when you upload your feature list, when you process your job with XCMS Online, the in-source fragments are going to be annotated. And this is what we're going to do. We're going to check all the features that we observe to see if there is a feature that matches a precursor in any of the available MS-MS spectra in mailing. If that happens, we're going to check if there are features eluting with this, this precursor here that match the peaks, the fragments in MS-MS data of that corresponding MS-MS spectra. And we're going to report this in the diff report of the XCMS Online job. So this is useful because we're doing three things. We're annotating in-source fragments. We are more sure that this feature here is a protonated species, because imagine that we don't observe any adducts for this metabolite, then it's more difficult to know where is the protonated species here. And it's interesting, as I say, to know where is the protonated species, because we can use that to fragment and then confirm the identity or even find the identity. And also we are providing a more robust putative identification of the molecule because we're using fragmentation data. So I'm going to cover very briefly some computational strategies that exist for MS-MS annotation. So as I said, we grab our features of interest, we fragment them with a cutoff, and then we compare the MS-MS spectra with MS-MS spectra of available compounds in public libraries. However, the problem is that only between 5 and 10% of the spectra that we have in those public libraries, only those public libraries only covered from 5 to 10% of all the known metabolites that we know. So that's a problem. So we came up with some alternatives to overcome that. One alternative is the use of in silico prediction, is to go from a structure to a MS-MS spectra. However, this is very difficult, very challenging in metabolomics because all the structures are very different. It's not like, for example, in proteomics that all the structures are composed of well-known sequences of amino acids. Here, the structure can be very, very, very different, so it's very difficult to come up with an algorithm that is able to predict any given structure. And there's been few studies that report the use of in silico, or that report methods for in silico prediction for mass spec. Now, the other way around, going from MS spectra to the structure, which I call it like reverse engineering, it's a little bit more difficult compared to in silico prediction. Still very challenging, but a little bit more easier. Sorry, a little bit more easier than in silico prediction, and attempts at precisely that try to do a computational spectral characterization of the observed peaks. And there's been many studies and many tools. We have many tools to do this spectral characterization or annotation, including MS Finder, CSI Finger ID, it's Finger, no Finder ID, IMET, GMPS also, and some use, for example, CSI Finger ID uses spectral tree methodology, which is that it grabs a structure and it says, okay, it could be fragmented here, here, and here. Okay, if it fragments here, we have this substructure. Okay, this substructure can be fragmented here, here, and here, and it starts computing all the possible trees that a structure can be fragmented to, and it uses that information to try to characterize this unknown MS spectra. There are other techniques that use some network methodologies, like IMET and GMPS, and those are based on the spectral similarity between similar molecules. And this is shown here in this next slide, where we have two molecules that are very similar, and their spectra, it's also similar. And of course, the difference here is carbon monoxide, and as I said, of course, the difference between the two precursors is going to correspond to this carbon monoxide. Also, the difference between those fragments is going to correspond to the difference of this carbon monoxide. So, if we can make use of those properties to better annotate our compounds. This is going to be explained by Rafa and Carlos. But there are some tools that make use of that to automatically or computationally take this fact into account and better annotate those spectra. Let's imagine that, for example, we don't have the spectra of the black. So the black spectra is our experimental spectra, the one that we have found in our samples, and we don't have the reference spectra for this one. But if we compare to spectra of a known molecule that we have, like guanine, then we can start computing the differences and, for example, assume that the difference here, since the difference corresponds to a carbon monoxide, we can assume that this new molecule that we are observing has a carbon monoxide attached somewhere. So as I say, this spectral similarity is implemented in Melin. It's called similarity search. Rafael, Carlos, and as I say, they're going to cover this. And there are some other tools that use network-based strategies. They're also rely on that fact that I just explained a moment ago, including IMET and GMPS. Specifically, GMPS, which is a database that also offers some computational tools or computational strategies to annotate spectra, performs something known as molecular networking, which is a visual way to actually perform this that I just explained, trying to group all these spectra that are similar and trying to relate them with the possible biotransformations between those molecules. So here it's going to compare these spectra, it's going to compare the similarity of these spectra between other spectra in the library, and it's also performs some kind of alignment based on the possible differences, the possible biotransformations between different spectra. So this is useful because let's imagine that the first spectra here is the one that we have, the experimental one that we have observed in our samples, and we don't have any match in the library. Now, if we project this spectra with all the library, we can find what are the most similar molecules to our experimental spectra, and then start to try to annotate our spectra in order to find a putative candidate so we can purchase the standard and confirm it. And the final technique for annotation, now I'm going back to MS1, but it also can be applied to MS2 data, is the use of retention time calibration. What we do here is try to predict retention times of molecules so that we can be more certain. Actually, retention time is an orthogonal property, so it's very powerful combined with mass information from the mass spectrometry to confirm the identities, or at least to get a more robust putative identification of the observed features. So the way it works is that we compute different molecular descriptors with prediction software, so databases, and then we combine these molecular descriptors with experimental values of known molecules that we have observed, or at least a training set, as we call it, and then we predict values for any other given metabolite. Now the problem of this is that the studies that have reported this, they report it mainly for reverse phase. There are some other studies that report that also for helic. The problem is that the training sets are very small, the ones that they've used, because of course, as you know, metabolomics is very challenging to obtain a list of standards, a big list of standards of correctly identified standards. We combine these, as I said, molecular descriptors with a training set, and we train a machine learning model to try to predict the retention time values for any other given metabolite. And it's also one of the drawbacks of this methodology is also that it's only applicable to one specific chromatographic method, the one that authors have used for training this machine learning approach. There are some authors, however, that have tried to overcome this second limitation. They try to use retention times from one method to another chromatographic method. So let's imagine that we have two chromatographic methods which are similar enough. And we have 50 molecules in one chromatographic method and 50 molecules in the other one. And 25 of them are common. So now we can construct this function. We can construct a function that relates the two chromatographic methods, and we can project the 25 that we have here to the other method and the other way around. So now we have more retention time values for the two chromatographic methods. And this is what those scientists came up with, and they created a library of retention times where users can upload their list of retention times with their chromatographic method used, and they can match their retention times to the ones that they have in the library and try to obtain more retention times from the other users that have uploaded the data. And finally, and with this slide I finish, if any of you guys are interested in the annotation of metabolites in XCMS, I recommend you to use this tool, ERA, which is an R package that we've developed 2 years ago. It performs the entire data processing workflow. It performs spectral extraction, so it does not work by peak picking, but it extracts directly the spectra, and it compares the spectra with available spectra of public libraries that you can actually download and load with the package. And that's it. I'll be happy to answer any questions that you have. Thank you.
So there is a question from the online for you, Xavier. So we've been chatting online for a little bit about the question, but I'll read the question as it is. How can we make the choice of adducts during our search, and how can we be sure of the annotation and the identification, as in such as the charge state of the feature? So to make sure that the charge state is correct for that feature, and how do you know that the adducts that it's chosen is correct during the annotation?
Well, in metabolomics, we assume that the charge is always 1. We may find some features that are charged, like it has a charge 2, but that's not that common. All the annotation tools that we have for metabolomics consider that there is a charge of 1. Some of them consider there is a charge of 2 too, but that's quite uncommon, and I don't know. So how can we be sure of the annotation? Well, that's why it's called annotation, because it's a putative. They give us a putative idea of what it can be, and then of course we have to manually by the standard and confirm the identification. We have always to do MSMS of data. So annotation is just that, annotation. Then the process that goes after annotation is identification, and we have to that's why annotation is so important, because it tells you what are the features that you may want to further fragment with MSMS, so that you can start figuring out what are the actual identities of those features. I don't know if that.
Have any other questions from the audience?
Go ahead.
Do you ever get useful structural information from the source fragmentation? When I say that, I mean more in terms of not just neutralizing
Can you repeat the last part? If you see multiple what?
If you have a more complex metabolite, a site with multi-sequence species, can you see cross-reactivity?
So with just to repeat the question to the online audience, he's asking if we get some sort of a structural information within source fragmentation. Well, that depends, of course, on the molecule. You can have molecules. You can find molecules that are quickly fragment in the inserts, but that depends, of course, on the molecule. So in some cases, you may have some structural information, but that's per general question, perhaps it's difficult to, or at least it cannot be generalized, right? That's going to depend on the molecules. Some molecules, for example, not even with fourth balls, you're going to observe any fragments. Depends always on the chemical structure. But in some cases you may, but just a few, I guess.
Xavier, we also have another question from the online users.
Mm-hmm.
They're wondering if how many are the fewest number of data points that you can use for the annotation, and how many data points would you be happy on? So, for instance, do you have to have a sodiated peak, a molecular ion, potassium adducts, and 6 or 7 different adducts and isotopes to be able to identify something, or are you happy with just 2? And do you think the algorithm, for the algorithm?
Of course, the more the better, right? I don't think there's a right answer for that question. At least if you have an adduct. If you have 2 or 1 adduct and a common loss, or if you have 2 adducts, it's always you can trust more an annotation if you at least find 3 relationships, right? The protonated, an adduct and a common loss, the protonated and 2 adducts, because as I said before, it's very easy to find 2 molecules, 2 features that which distance between them is similar to the known adducts that we are considering for annotation. Go ahead.
Compare the features that the software cannot find in isotopes.
What's that? Sorry.
Compare the features, known features that software cannot assign in isotopes.
So what do you do with features that you don't find any? Well, then you have to start perhaps observing all the features that allude at the same retention time. Perhaps start with the most intense one, then perhaps move to the other one, the less intense. Try to fragment all this and see how you can identify these molecules. I don't know if Rafa or Carlos have any idea on how to solve when you observe a feature that there is no adduct. This is a regulated feature, and you have no annotation. You don't know if that's an adduct, if that's a protonated species. What do you usually do when you find those cases?
Like you said, from case to case,
Mm-hmm.
that you assume, let's say it's the adult for another feature,
Mm-hmm.
but it could be also the adult for that feature, and you don't need to take those things into account.
Uh-huh.
So it's hard to give you an exact answer because that will vary for each different feature, for each different compound.
Just for the online audience, Rafa said that this is gonna vary, of course, depending on the cases. So you have to figure it out by yourself, I guess.
And Xavier, one more question from the online people.
Okay.
They would like you to talk about ERA, how it does the deconvolution, and how it figures out the MS2. They ask, which I know.
Well, in XCMS we don't have MS2, so we use electron impact. So we already have a fragmentation. All the molecules are hard. EI is a hard ionization source, so we have the fragmentation already. IDA, what it does is it uses a multivariate algorithm based on blind source separation to extract the different spectra of the underlying metabolites in the samples, and then it compares those spectra with those that are available. Actually, we use the mass bank and the GOLM metabolome database to compare the spectra, the convolved spectra by IDA with those databases to find putative identifications of those metabolites.
All right. If we don't have any other questions,
Thank you very much.
thank you very much, Xavier. So now I'm going to pass it over to back to Bill, who's going to be speaking to us about quantification and targeted MS.
Metabolomics. All right.
Thank you very much.
Hello again. All right, so here we're going to talk about quantitative metabolomics or quantitative mass spectrometry or targeted metabolomics. So we've seen this slide earlier. This describes the general workflow in our lab. You have two sample sets that you extract, analyze, one's helic and one's in reverse phase using C18. The idea here being to observe as many metabolites as possible in a given sample. Once you have this data, you then process that using our XCMS chromatographic alignment software, picking out M over Z values that differ the most, using exact mass measurements and MS data. You then compare it to databases like Metabolites and others, get an identification of this compound, and once you know what this compound is, the next step is how much of it you have in your samples. So targeted metabolomics involves knowing exactly what you're looking for, unlike untargeted, where you don't know. And once you know what it is, how much of it do you have? And to answer those questions, use a triple quad mass spec. For the untargeted work where we don't know, it's important to have the high accuracy instruments like the TOF instruments, the Orbitraps, the FTICRs. Those are really helpful in identifying unknowns. But once you have now what you know what you're looking for and you want to measure how much is there, these are the instruments of choice. So you can do many things with these. These involve a first quadrupole, a collision cell, which is often been called the second quadrupole, and then the last quadrupole. You can do things with instruments like product ion scans, where you just isolate a single M over Z value with MS1, fragment it in the collision cell, and then analyze all the product ions. You can look for classes of compounds, like compounds that have phosphate groups on them, by letting a bunch of things pass through MS1, fragment them in the collision cell, and only letting M over Z values of 79 pass through the MS2. This is the second quadrupole. But if you want to actually measure how much you have, the technique we use here is multiple reaction monitoring. In this experiment, what we'll do is we'll set the first quadrupole, isolate on a particular fragment ion. In this example, either 210 or 350. We'll then fragment these in the collision cell, and then we'll set the second quadrupole, MS2, to isolate on a particular fragment ion, either 91 for this example, or 26. So this 210 to 91 and 350 to 226, these are called transition states. Go back, no. Right, so given that example, only compounds that have a given parent and a given product make it all the way from here to here. Now, why this is useful, I can demonstrate here. This is a scan using the single quad in selected ion monitoring mode, like I talked about earlier, where we're only scanning for one M over Z value. This sample is a serum extract, so there are hundreds, if not thousands, of compounds present. So it's not surprising we have more than one compound of a given mass. If the compound you wish to measure elutes somewhere here where it's nice and clean, then that isn't much of a problem. But if it's eluting somewhere in here, we have many other isobaric species eluting, your quantitation may not be so good. You can take the same sample, the same extract, looking for the same compound, run it on a triple quad in MRM mode, and this trace now looks like this. So we have a much cleaner peak here, and you're much more confident of the quantitative answers you're going to get if you're looking at a peak like this. So if you want to measure how much you have in absolute amounts, like how many nanogram per ml of this compound do you have. Internal standards are very important. If all you're interested in is relative quantitation, does sample A have 3 times more than sample B? Maybe not so much, but for hard quantitation, nanogram per ml, you will definitely need to add internal standards. And the reason we'll need to add internal standards is there's always going to be losses during the extraction procedure, right? There's going to be matrix effects and ion suppression effects when you go to the analytical end of it. So the ideal internal standard to take into account for those things will be chemically very similar, but just different in mass. So the best internal standards are going to be deuterated versions or isotopically labeled versions of the compound that you're looking for. They're going to behave identically chemically. They're going to extract the same. They're going to chromatograph the same. The only difference they have is the mass. Deuteration's here, hydrogen's here. The C13 labeled are probably the best, but they're also the most expensive. Deuterated versions work just fine. Just make sure this is stable and won't get swapped out at some point during your process. So when we do an internal standard calibration, we're not looking at our internal standard quantitation. We're not looking at the absolute areas of the analyte and comparing those to the standard. What we're looking for is the ratio of areas between the analyte and the internal standard, because we're going to have losses in the extraction procedure, signal suppression effects on the MSN, ion suppression effects going there. So the actual area, absolute area of this compound, the analyte, compared to that of your standard, may be less, but the ratio of the two will be the same. This is how internal standards take into account losses during sample prep. So when you go to add internal standards, since looking at ratios, the amount of internal standard you add to your samples needs to be the same as you add to your standards, since we're looking at the ratios. When you go to add these internal standards to your samples, for fluid samples, it's pretty straightforward. You add the appropriate amount into it before you begin your extraction process to take into account losses. For solid samples, we don't inject it right into the tissue itself. There we are. We don't go right into the tissue itself. Instead, we'll add it to our extraction fluid, and we'll add it to the homogenizer here. The idea being that the concentration of the analyte inside the tissue and the internal standard inside the extraction solution will reach an equilibrium by the time this is done. The net effect of adding internal standard, taking into account matrix effects and ionization suppression effects, is that you tend to get very, very linear standard curves, which makes quantitation very, very handy, much more reliable, and much more believable. And the last thing I want to touch on here on quantitation is that when you do set up your standard curve, you want to make sure that the levels you have here for your low and high standards, they're going to bracket everything that you have in your sample. So you don't want to have your curve and then measure your sample and have the response being somewhere out here. You want to have all the responses being within the curve. Pick your standards to bracket everything that you're going to find, you expect to find in your samples. And that, in a nutshell, is overview of how we use mass specs to quantitate and generate us numbers. Happy to answer any questions on this. Thank you.
So, Bill,
Yep.
You have 2 questions from the online system.
Wonderful.
Run on. The first one is, I've heard that people generally don't like to use mass data for quantification, but UV is considered more trustable. What would your thoughts on that be?
UV is wonderful for quantitation, but it's not as selective as a mass spec is. So yes, UV is good, but all you're looking at all compounds that absorb at a certain wavelength. And you're not getting mass data, and you're not getting fragment data as well. So by using triple, you get parent mass information and unique product ion information to quantitate just the compound that you want to measure. Sure.
And they also are wondering, would a distereoisomer mixture be considered a standard for internal standards?
Generally not. you probably want, I mean, if what you're measuring is one, perhaps, but you want to make sure it elutes at the same time. And so you want to be chemically as similar to the compound that you're measuring as possible. And if you have that mixture, that could perhaps form two different peaks on your column. So the concentration you're adding, what you may be observing is half of what you're actually adding. Yeah.
Any questions from the audience?
Yeah,
Yes.
sure.
Is it possible to perform MERM experiment using a QTOF system or only in a triple quad pole?
It's only a triple quad because QTOFs, they have the initial quadrupole, they have the collision cell, but they don't have that second quadrupole. It's just an ion guide. It sends all the fragments into the flight tube. Only triple quads have that second quadrupole. And I think the reason for that is, I was very curious. I would love to have a triple quad that had a TOF on the end, so I can get that, all the benefits of an MRM experiment and the accurate mass measurement on the far end. But when compounds leave a quad, they're moving in a spiral form, like this. And when they go into the flight tube, they all have to enter in at the same point in space, because you've got this pulsar that's going to send them up the flight tube and then back down. And all you're doing is measuring the time it takes for it to traverse that distance. And if you have compounds coming in a spiral, you may have some coming in low, you have some coming in high, same compound, they get the pulse, but it is a different time, so they'll come up as being different masses. So, because QTOFs don't have that second quad, generally you can't use those for a true MRM experiment.
Why did you say that deuterated internal standards are preferred?
The isotopic label ones are preferred because they're going to behave chemically exactly the same as the compound that you wish to measure. So any type of losses that your analyte is going to suffer during the extraction process, your isotopic label is going to suffer the same. They're going to chromatograph at exactly the same time. So if there's any kind of matrix effects going on in the column or ion suppression effects you may see in the spray chamber, they will experience them both the same.
Is there a difference between deuterated and other stable isotope?
C13 would be the other stable isotope I'd use, and I think that's stable. That is probably the best one, but it's the most expensive one, and it's much easier to buy isotope deuterated compounds than it is to buy C13 labeled compounds.
All right. Thank you very much, Bill.
Sure thing. Thank you.
So on that note, I'm going to pass over to Rafa, who's going to be talking to us about identification using fragmentation data. I know many of you have many, many questions on this. So Rafa.
All right. Thank you for the introduction. Like Paul said, I'll talk about identifying molecules with MSMS data, and that's still, in metabolomic studies and in targeted metabolomic studies is still the big obstacle. It's definitely a challenge, and something we're trying to today give you like a couple of tools, resources, and tell you a little bit about it, how you can go whenever you have a feature that seems really, really, I guess, interesting in terms of statistics, about the phenotype that you're studying, but you simply just cannot identify it. But before jumping into that, let's talk about what actually means to identify a molecule or what the differences are. And according to the MSI, there are several levels of identification. So levels 5 and 4 are 5 would be the exact mass, and with that exact mass, you can calculate the molecular formulas, the possible molecular formulas for that particular feature. So that is relatively easy to get. The exact mass, you get it from your analysis, and the formula you can calculate that most the softwares that you use for your XCMS instrumentation has some kind of tool that can calculate that, and if not, there are other tools that can do that online. So then level 3, it's for that you have MSMS data or some experimental data that can tell you a little bit more about the possible structures for that compound. They're called tentative candidates, and as you can see here, you have an idea of what the compound can be, but you're not sure where the position of that hydroxy or that nitro group are. But you could have a really good idea of I guess the main the main structure of the scaffold of the compound. What we strive and struggle, and it becomes a little bit harder, is to get to these two levels. Level 2, the probable structure, for that you have a sort of like a match, or you find that compound in a database, or you have very good diagnostic evidence, like for example, phospholipids. They are it is really well understood how they fragment, so you can I guess be more confident of that putative identification or probable structure, even if it's not in a database. But then, to be able to get to level 1, the confirmed structure, for that you need two things. You need the reference, you need to have a standard material for that, and have orthogonal data. And in that case, this is what RT means, retention time. You need to run it on the exact same conditions, same column, the same instrument, and make sure that it is that feature that you're interested in. That is the only way that you can get to a level 1, a really confirmed structure. So whenever we try to identify a feature, in many cases it can seem something like this. We have an M over C value. We're trying to get to the metabolite ID, and for many compounds, especially databases increasing every day, it could be sort of represented by this biker here going up a relatively comfortable slope all the way to the end goal, which is the metabolite identification. But for some features, getting to the identification, it looks more more like this, and sometimes we give up along the way. But yeah, getting all the way here is definitely a challenge. But with everybody, many labs around the world are working to improve this and to make this simpler. So I'm going to talk about more the MSMS side, how you can use your MSMS data to try to identify your compound, or at least try to reduce the number of putative metabolites that you have. In case, imagine you have 100 putative metabolites, you cannot go and get all. Well, you could get all those 100 compounds and see if that's the metabolite that you want, that you actually have. But if there's a way that you can narrow it down and bring it down to just a handful, it's something more manageable, not only in terms of time, but also in resources. So what you do is, first you compare. You want to compare your MSMS data to whatever's online. So you just look in the different databases and see if you can find MSMS data for those putative metabolites that you have. The answer will be pretty simple. There is or there is an MSMS data for those compounds, and let's just stay here on the fortunate side, on the yes, that you found some MSMS data for that. And then what you do is just simply compare. Does it match? Yes or no? Again, let's stay on the easy on the fortunate side, where actually it does match. So what you do then is, going from the level 2 to level 1, where you confirm that with the standard, right? But what happens if it doesn't match? Then you go back to, there's no MSMS data available for that particular compound. And for that, we have created some tools that are available in Medlin, which leverage the large amount of MSMS spectra for many compounds. And I'm going to show you these two tools, fragment similarity search and neutral loss search. And what they do is they provide information on the molecular class or molecular type. For that, I'm going to show you that I'm going to use an example. I think it's going to be easier to show you with an example than just give you the sort of like the theory behind it. So let's start with fragment similarity search. This is what the interface looks like. On the left-hand side, you can see you can enter the different fragments that you got from your MSMS data. You can enter other parameters such as the tolerance in ppm, if it's positive or negative, and the threshold for intensity. And what it does, it's going to go through the entire database and look for fragments that actually match with other molecules. And what you're trying to do is, like the name says, fragment similarity search is going to look for fragments that are similar in other compounds, to try to get you an idea of what that compound can be. And I think Xavier explained a little about how that works. Then the return is going to be a list of metabolites and small molecules that have those fragments within that ppm range, and it's going to list them in terms of how many it matched. In this case, 3 out of 4 is going to be before 2 out of 4. So you can they're going to be listed in terms of how likely or how similar they are to each other. So to show you an example, here on this spectra here on the top, these are experimental MSMS spectra for a particular feature in positive mode at 20 volts. After performing the fragment similarity search that I showed you in the previous slide, we get a centohumol that was I guess the top hit. And we can see that the fragments, this is what it's in the database in Medlin at 20 volts. You see the fragments do match quite well. We had a hit of 3 out of 4, and the reason is here this little, this very small fragment here, it was below the intensity threshold that we were searching. So if we would have lowered that threshold, it would have been 4 out of 4. So this is the compound centohumol, and since it looks really good, this is the precursor for our feature, and this is the precursor for in the database. So we could say it has some kind of centohumol type structure. It has some kind of scaffold, the centohumol scaffold. What we don't know at the moment is what is the difference from here to here. What are those chemical structures? What are those moieties? What accounts for this mass difference from here to here, which actually is 176 Daltons. So what we can do, since we don't see other fragments, we can search for this difference with neutral loss, the other tool that I was telling you about. And we do that here, also in the Medlin webpage. Similar to fragment similarity search, we enter the neutral loss here with the certain parameters, and we look for that. And this also, what it does is leverages the large amount of MSMS data found in Medlin for many molecules, and it just looks where is this neutral loss observed as well. You get all these different hits, and you can filter them by name, mass, ppm, and many other parameters. And you can see the structures here on the right-hand side. And from the, I think, over 100 compounds that we observed with this neutral loss, when you start going through the list, you start noticing some type of I guess structures that repeat themselves. For example, here this one has a glucuronic acid. This one also has glucuronic acid, and this one has glucuronic acid. And if you go down the list, you're going to find that many times. So, well, you don't know that for sure because you don't have any data, just that neutral loss. But since it comes up so often, we can think, okay, probably or likely, or it could be a glucuronic acid molecule here attached to the centohumol. And with this data, again, we don't know. We're just reducing the number of putative metabolites of what it could be, getting just a better idea of what type of molecule we're dealing with. This glucuronic acid could be in another hydroxy group, but we're just placing it here for the moment. So with this, what we're able to do is get an idea of what type of structure that was, even though it wasn't in any database, and we can get an idea of what the differences are or could be to the molecules that are actually found in databases. So it helps you reduce the number of putative metabolites in case you want to go get the standards or need to go get the standards, not to get 100, but to just get a few. Or if you're thinking about synthesizing them, synthesizing 100 compounds is not the same as trying to synthesize a couple. So what we're trying to do here is just like narrow it down and see what can explain the MSMS pattern that you observe. Now, I want to show you another example that is a little bit, I guess, the data doesn't look so like to match so well. And the other reason why I want to show you this next example is just to show you what a small modification in a relatively simple molecule can do to the fragmentation, to the dissociation patterns of the molecule. For that, the example that I chose was N-acetylmuramic acid. Let me just walk you through this again. We got a feature. This is our experimental MSMS. This is our precursor. After looking at this mass in databases, we thought that, yeah, N-acetylmuramic acid was one of the possibilities with a bunch of other molecules. We performed the MSMS experiment, and we did fragment similarity search, and also neutral loss from here to here, and it all came out that it could be, the neutral loss could be an acetyl group, and many of these fragments do match that of muramic acid. Now, if you compare to the previous example that I showed you with centohumol, you could see, yes, there's definitely some fragments that do match, but there are many differences, particularly here in the lower M over C. There's some fragments that we don't observe here at all. The intensities here are much lower. These ones don't show up. But the biggest difference would be this this base peak here, this very prominent peak that we find in our spectrum, but it was not found in the standard for muramic acid. You just don't see it here. So even though it looks considerably different, just by having a small modification like this acetyl group here, you could think, okay, yeah, it's probably that or it's probably something else. And looking at the structure, you could see maybe there's some other modification or carbohydrates are different. So it could be something completely different. But we still got the standard. We thought, okay, we might as well. And then once we did that, when we confirmed that this is then the spectra from our experiment, and this is what we got from the standard, and then you see it does match quite well. But you see what a very small modification in a molecule can do to alter the dissociation pattern of a molecule. And that is why generating or creating models or predicting models of a molecule's fragment is so challenging and has not been able to be done at a level where we just don't need to have these databases. It's still really hard to understand. So this takes me to the next part. So the next part that I will show you is like some tools and some resources that you can use to identify molecules from scratch. I'll talk about some informatic tools, some models, also how you can use the literature, and some fragmentation rules to how to try to identify or interpret your MSMS spectra. So I will not go into much detail about these tools. I think Xavier mentioned quite a few and did really well, can do a better job at explaining what they do. But in general, what they do is they use with machine learning algorithms and some MSMS spectra, some databases. They learn trying to predict how a molecule can fragment, or from a fragmentation pattern try to get to a possible structure. And these are I'm just listing here 3: MEDFRAG, CFMID, and CSI finger ID with the references. There are many others, and people always, many research groups are working hard on these, and they're always creating new tools, improving them. So I would just encourage everybody to take a look at them, and again, not just these 3, but there are others, but we just couldn't go over all of them. The next resource that I think is really important, and I don't think is used that often, is literature. If you just look up MSMS experiments or LC-MSMS experiments or spectra in PubMed, you're going to find tens of thousands of papers. And in there you can find really good MSMS data. Not all of the data will be high resolution data like you would get from these databases. They could be triple quad data, but again, you can use all these transitions or all these fragments and compare to your data and see if it matches, if the fragments that you see other people have observed with those fragments, and try to reduce or get a bit of idea what molecule you're dealing with. So it's a good resource, and definitely I would encourage people to use that. We have used that before, and I chose this example. I thought it was very interesting. It was something like 6 months ago. We had this fragmentation pattern, this fragmentation for this feature here on the top. And after looking at MS1, this was one of the possibilities. We went into the literature. We found a couple of papers that had actually looked at this. And then we found the MSMS spectra for this compound. Even though it's a different collision energies, the fragments do match quite well, which then encourage us to just go get that particular standard, and we were able to confirm it both with retention time and MSMS data. So it definitely made the decision easier to just go get this one versus going and getting several compounds and see which one it could be. And we found, since we found that in 2 papers, it just increases your confidence that is actually the spectra that you're observing as well. And another type of resource is, for example, dissertations. Some dissertations are available online, and if you think how much experiments or how much data was collected during grad school, but it was not published. A lot of it ends up getting into the appendix or just as a figure in dissertations. And you can find a lot of MSMS spectra in there as well. To show you how useful that can be, I want to go back to the first example of xanthohumol glucuronide. And in this dissertation, we found the MSMS spectra for this compound here, for the xanthohumol glucuronide, and it does match quite well with our spectrum in the first place. And in this dissertation, they actually found that the glucuronide being in this hydroxy group, it creates this spectrum, but in the other two hydroxy groups, you get different MSMS spectra. So even it can tell us that it actually this glucuronidation is found in this hydroxy group. So it's pretty good research to go and look in there whenever you just don't find anything else in any database. A word of caution is definitely necessary here. You have to think that all this, whatever is in papers or in dissertations, you're depending on just that operator, that the instrument was working fine, it was well calibrated, that everything was correct. So just using just one of those resources is not just maybe the best idea, but it definitely helps you reduce the number of putative metabolites that you can have. And also look for other papers and other places that actually could find and corroborate what you first found in that first paper or dissertation. So in most cases it is really good, reliable data, but just think about that. It could be not correct. So the next research, or the next tool that I want to show you are fragmentation rules. Even though they're called rules, they're not always fulfilled. You could call them more guidelines. And there are 4 rules that I want to show you today. And then I'm going to show you one example for combining all of those 4 rules. I think it's going to be more simpler showing you one example than just showing the rule. So the first rule is that fragmentation results in a charged species and a neutral species, as a charge cannot be split, right? So you have A plus A and B, and when it splits, the B ion is the one that you would observe. If you observe both B and A, those come from 2 different ions, where one actually passed the charge on to the B part and the other one to the A part, but not from the same molecule. You cannot see that. The second rule is the products will depend on the strength or the number of bonds that need to be cleaved to generate that ion. And aliphatic are less stable than aromatic or conjugated C systems, for example. And a C heteroatom bond is less stable than a carbon-carbon bond. The third rule is that fragments from protonated and deprotonated species have an uneven number of electrons, and with that you can use the nitrogen rule. This rule says that a fragment with an even M/C value has an odd number of nitrogen atoms, and vice versa as well. If the M/C value is odd, you will have an even number of nitrogen atoms. There are some exceptions, it's like a loss of a halogen for an aromatic compound, but in general they tend to be fulfilled. Again, I know it's like showing you a lot of rules right now, but it'll make more sense when I show you the example. The fourth rule is a little bit more complicated, but in general, the cleavage of a carbon with a heteroatom results in the charge migration to the alpha carbon, or in charge retention to the heteroatom by proton rearrangement. And in some cases, you can observe both. And how you can confirm that is with this simple math equation. The sum of the nominal masses equals the nominal value of the M plus H plus adding plus 1, or the M minus H minus 1. So I know it's a little confusing at the moment, but I'll walk you through it with this next example. The example I chose for that is enolyl taurine, is this molecule right here. Here you can see the MSMS spectra for it. This is the precursor, the M plus H, and the mass is 390. You observe 2 fragments at 262 and another one at 126. So we know this is the molecule. We see the mass is 390, that means it's an even number, so it must have an odd number of nitrogen. There's only one nitrogen here. For these two fragments, we observe a 265 and a 126. This one is an odd number, so you must have an even number of nitrogens. Even in this case, it can be 0, 2, 4, and so forth and so on. The 126 is an even number, so that means it has an odd number of nitrogens. So we only have one nitrogen, so we know that this fragment must contain the nitrogen. The other rule was that a C heteroatom bond is more likely to cleave than a carbon-carbon bond. So the place where it could more likely cleave would be here, 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 or here. So we know that the fragments that are generated, one has the nitrogen, the other one does not. So the more likely it either fragments here or here, right? But when we look at the masses, then we can know where actually the cleavage occurred, and we get these two structures. Like I said, in this case of the 265, the charge could be passed on to the alpha carbon, which would be this one. Then you get this fragment at 265, or you get a charge retention by proton rearrangement, and it goes then to this nitrogen here, and then you get this fragment here of 126. Remember that formula that I mentioned to confirm that? It is this, that the M plus H, since it's in positive mode, M plus H plus 1, which would be 390 plus 1, should equal to the mass, should equal exactly to the nominal, to the sum of the nominal mass of the two fragments, which actually is 391, should be 260, should equal to 265 plus 126 is also 391. So you can confirm that this is how this molecule fragment, and you can use this to interpret your MSMS experiments. So with these tools, I hope you can now reduce the number of PDFIDs that you have and narrow it down to just a handful, and not try to get that many standards, and really encourage you to push and try to get those molecules. In many cases, there are commercial standards for the molecules that you think you have identified or you are interested in. If not, analog compounds can also help you increase your confidence that that's the molecule that you have, like a shorter carbon change in like a long fatty acid, for example. If you don't have exactly oleic acid, but you have palmitic, that should give you very similar fragmentation as well. So take that in mind. And in conclusion, is like I said, confirm with the standards whenever possible to get to level 1, not just use the databases. That would be a level 2. Try to get to the standards and use orthogonal information like retention time with standards. And in publication, it's always good to indicate the level of identification to know just how confident are you of that identification. And there are many other resources that can help you interpret your MSMS data. Again, we're able only to go through a few because of the time, but there are many other really cool informatic tools out there, and other databases that have other tools as well online that I definitely encourage you to take a look at. And with that, I'll be happy to take any questions.
Do we have any questions from the audience? For the search of literatures and the specifications, is it inside the method or somewhere else?
No, just look at Google Scholar, SciFinder, PubMed. Just try to find for that metabolite. Right? There's no link to those metabolites in the database. No. Sorry?
Are there any created fragmentation methods other than CID, such as EID or
We don't have that in Medlin. The largest databases are definitely Electric Impact, which was mentioned for GC. NIST is big. mostly CID, and that's Medlin, and there are other ones out there, but definitely Medlin is the one that has the largest number. I think a HCD type fragmentation from thermo instruments are also available. For ETD, I don't think there are. I think that the use of ETD for metabolomics, it will be like very specific because you need at least doubly charged species. So I think Xavier was mentioned that in the majority, most of the time we have a singly charged species, unless they're considerably larger, and therefore there's not that many. It's not widely used, and I must say I don't know of any database that has ETD databases or data for small molecules or metabolomics. I don't know if you think there's one.
I mean, from my understanding, ETDs most of the time normally proteomics and much larger molecules. Normally, CID is used in metabolomics just because it's a softer fragmentation, and so if we use something like ETD, then it would blast the compound apart much more, and so CID gives us large enough fragments that we can still have enough information to try and piece it back together again.
It would be interesting to look at ETD for like simply carbohydrates.
Yeah.
But yeah, that's where it would be used the most, I would think. But yeah, I don't know if there's a database for that. It would be interesting. Is there any questions?
So we also have a question from the online asking, is there a hydrogen rule in the same way as there is a nitrogen rule for fragmentation?
I think with hydrogen, there are some other rules. I just went over a few, but the thing also with hydrogen is just hydrogen rearrangement. They can pass on so quickly. It becomes a little bit more challenging. I think these are like the simpler ones that you can easily use for your identification purposes.
And then I'm also going to answer one, and you're welcome to jump in, Rafa, if you want. The question is, what type of scoring systems do we have for annotation in terms of spectral matching? So in terms of spectral matching, one of the most used algorithms or scoring systems is the cosine similarity or dot product. You may have heard of it. It's used if you go and do a NIST XCMS search. It's what will be used. It's a very, very simple score. Basically, it's essentially regression. It puts one spectra on one axis, on the x-axis, and the other spectra on the y-axis as a vector, and then you score the two between each other. That gives you the cosine similarity. There's other much more complicated and sophisticated scoring systems, such as an algorithm which came out a couple years ago now called XRank. XRank is a very cool algorithm. Basically what it says is, given the current database, and this is a little bit of a caveat of it, is that given this current database, it will go through that database and it will find the peak which is the most unique for any one specific compound. So let's say, for instance, I don't know what the caffeine spectra looks like off the top of my head, but let's say that it has a peak of 120. And this peak of 120 point only ever comes up in the database for caffeine and for nothing else. So now, as far as XRank is concerned, if you have an MSMS spectra that has 120 point in it, you're automatically going to say that this is caffeine. Without seeing anything else, you can say that it's caffeine, because this peak is 100% identifying to this spectra. Now, of course, as mass spectrometrists, we'll start to raise a couple of issues with this and start to say, aha, but your database isn't full and complete, so there may be something else that has the mass of 120 in it, and so that causes some problems. And it's also unlikely that it's going to be that specific within your ppm range when you start to get into larger databases. So what it starts to do is it also starts to rank them, and it ranks them by the largest intensity. So it says peaks that have large intensities in the fragmentation have the most information on them. There's a bunch of different other algorithms out there, and there's some really good review papers by Sebastian Broker, which I recommend you all to go out and see. I close that so I can't check any of the... I've closed my computer for those of you who can't see online, so I can't check any of your other questions if you've asked in the last few minutes. But unless we have any other questions from the audience... Okay, I'm going to pass it now over to Carlos. Thank you very much, Rafa. Who's going to be speaking about metabolite identification using isotope standard or stable isotopes standards. So, Carlos.
Thank you very much, Paul, for your introduction, and thank you everybody to come here on site and those who are following our streaming emission. So, in this presentation, I'll talk about some aspects of isotopes that can be used for the identification of molecules, that can be used as a complementary approach for the techniques that Rafa explained before. So my presentation will be divided in 3 sections. In the first, I'll show you how to use the endogenous isotopes of atoms and molecules to rule out some putative metabolites in identification. In the second, I'll show you how to generate isotopic data using uniformly labeled microorganisms. And in the last section, I will show you how to use that isotopic data to identify 3 unknowns. So let's start with the first section. So as everybody knows, isotopes are atoms of the same element with different mass due to the presence of neutrons in the nucleus. Since biomolecules are composed essentially by these 6 types of atoms, in this table I'll show you all the stable isotopes that can form the biomolecules with their relative abundance in nature, highlighted in red the 3 most common, the deuterium, carbon-13, and nitrogen-15. So due to the presence of these isotopes in nature, when we observe the mass of a metabolite in the mass spectrometers, we don't only observe the monoisotopic mass, that would be the addition of the most intense isotope of all the atoms that compose the molecule, but we also observe other peaks whose intensity depends on the molecular formula of the metabolite. And the combination of the monoisotopic mass and all these other peaks is called the isotopic distribution of a feature. So, can we use this isotopic distribution of a feature to unambiguously identify the metabolite? Of course not, but we can gain some information only using that information. So for instance, we have this example here. We have this unknown feature with a M/C ratio of 241.03, and this is its isotopic distribution. So when we search for possible metabolites with that mass within a tolerance range of 5 ppm, we get that this mass can correspond to these 3 molecular formulas. So I would like to ask you, would you be able to rule out any of these formulas, or 2, or maybe the 3, just observing the isotopic distribution? Any idea? The answer is definitely yes, we can. And we can, and I'll provide you now more help, because if we observe this table, when we have this M+2 isotope higher than the M+1 isotope, it's very likely that the molecule contains a sulfur atom. And why? Because the most abundant isotope in sulfur is not the M+1, it's the M+2. And actually, this is the most abundant isotope in nature. So it's very likely that molecules with these isotopic patterns contain sulfur. So I would say that our metabolite has not this formula and could have, or the first or the second, probably the first one because it contains 2 sulfur atoms. Actually, we can simulate in silico the isotopic distribution of those 3 formulas and observe that the most similar to our unknown metabolite is this one. So then we confirm by XCMS that this metabolite was cysteine, that of course contains these 2 sulfur atoms. We can use other consideration regarding isotopes that can help us for the identification or to reduce the number of putative candidates. Another is the mass defect. The mass defect in mass spectrometry is defined as the mass difference between an element exact mass and its nominal mass. By definition of atomic mass unit, the mass defect of carbon is 0, the mass defect of hydrogen and nitrogen is positive, and on the other hand, the mass effect of oxygen, and especially phosphorus and sulfur, is negative. So we can think that molecules containing a great number of hydrogen or nitrogen atoms will have a positive mass effect, and molecules containing a great number of oxygen, phosphorus, and sulfur atoms will have a strongly negative mass effect. So for that reason, I asked Xavier to plot 5,000 random molecules in Medlin and plot the mass effect as a function of their monoisotopic mass. And we have a figure like this one. As you can observe, only few of these metabolites have a negative mass effect. And actually, if we check the formulas of these metabolites, we find that are metabolites with a low number of carbons and therefore of hydrogens containing a high number of oxygen, phosphorus, sulfur, and halogens. If we observe this high mass range, where all the lipids are, we observe that the slope of the correlation between the mass effect and monoisotopic mass is higher than in this low mass range. And that's because lipids are composed by long hydrocarbon chains that introduce a highly positive mass effect. And actually, if we search for some metabolites here in the high mass effect range, we observe that all of them are lipids containing those hydrocarbon chains. So here I ask the same, can we use the mass effect of a metabolite to unambiguously identify it? And the answer is again, no. But at least we can use this information together with the information provided by the mass effect of the fragments of that metabolite to rule out some possibilities and help us with the identification of the compound. For instance, we have this unknown feature with this mass of 122.02. So if we locate that mass in our previous figure, we see that from all the molecules with a mass of 122, the mass effect of this one is in the low range. So we can hypothesize here that this molecule will contain a high number of oxygen, sulfur, and phosphorus atoms and a low number of carbon and hydrogen. And actually, we search for that mass, we get that the only possible formula is this one that only has 3 carbons and has 2 oxygens and 1 sulfur. And the metabolite that is better represented by this formula is the amino acid cysteine. So once we have the putative metabolite, we can use the mass effect of the fragments of the experimental MSMS of this feature, unknown feature that we have, to help in the mechanistic study of the fragmentation. Starting from the most intense fragment here, we observe that the mass effect compared with the mass effect of the parent ion is about 0.03 lower. And 0.03 or minus 0.03 is the mass effect by sulfur. So it's very likely that this fragment will contain this sulfur atom, as it was confirmed later. For the fragment of mass 76.02, we observe that the mass effect is slightly lower than the mass effect of the parent ion. So it's probable that the sulfur is also contained here, but maybe with other atoms with positive mass effect that can counteract that negative mass effect by sulfur, as it was confirmed later because this fragment corresponds to this structure. This fragment, in my opinion, is the easiest to explain because here, in a mass difference of only 36, the mass effect is about 0.04 lower than the mass effect of the parent ion. So this means that probably not only sulfur is contained here, but probably also one or the 2 oxygen atoms. And actually, that fragment corresponds to this part of the molecule. And finally, for this fragment, we observe that this is the lowest fragment, but the mass effect is even higher than the mass effect of the entire molecule. So probably this will be composed only by atoms with positive mass effect, like hydrogens and nitrogen, as we confirm later. So at least using this limited information, that can help us to study the fragmentation spectra of a feature. And finally, we confirmed that this fragmentation spectra corresponded to cysteine. The last aspect I would like to talk about the isotopes is their role in the presence of multiple charge ions in metabolomics. As Xavier and Rafa mentioned before, multiple charge ions are not very common in metabolomics. But for instance, for this kind of molecules, cardiolipins that are very, very important phospholipids in the heart membranes, these double charge ions can appear. So the way to differentiate between single charge ions and multiple charge ions is just observing the isotopic distribution. If we have a single charge ions, we observe that the difference between the monoisotopic mass and all these isomers is about 1 Dalton. And however, if we have a multiple charge ions, we observe that this difference is lower than 1 Dalton. Since here we have a double charge ions, the difference here is 0.05 Dalton. So which information can be extracted from the presence of multiple charge features? This can be used for annotation of features coming from the same metabolite, of course. Can be used to detect the presence of 2 or more highly ionizable functional groups, like phosphates in negative, like in the example I showed before, or amines in positive mode, or can be used for the discrimination of features coming from single charge molecules. So coming back to the example of the cardiolipin, when these molecules are analyzed in negative ion mode, the single charge and the double charge ions produced are very similar. So we can consider either for the analysis of these compounds, which is great because when we typically make these profiling experiments in untargeted metabolomics or lipidomics, our highest range is about 1,000 or 1,200 Dalton. So in that case, the single charge ions would be overlooked. So since these molecules are also ionized as double ions, we can take the other ions that appear in this range of 600-700 to study these molecules. And I'm showing this asterisk here because this mass is the same for the major phospholipid class PE. So in that case, especially if we don't have a good chromatography and a good resolution in our instrument, those ions can be confused. But even in that case, just observing the isotopic distribution, we will be able to distinguish between the double charge ions coming from cardiolipins or the single charge ions coming from PE. So as a summary of this first part of the presentation, we can use this limited information, of course, provided by isotopes of atoms and molecules to at least reduce the number of putative metabolites and help in their annotation. So the second part of the presentation is the generation of isotopic data using uniformly labeled microorganisms. So as I mentioned before, the use of these stable isotopes can be used to annotate some features and help in identification, but the information provided is very limited. So at this moment we propose, okay, why don't we generate molecules where all atoms are stable isotopes, the so-called uniformly labeled metabolites. So with this approach, we think that we could get much more information for the identification of compounds and maybe at expenses of an increase in the complexity in data generation and analysis, of course. And the vehicle to accomplish this is the growth of uniformly labeled microorganisms. I don't want to enter into much detail into this, but to grow these uniformly labeled microorganisms, we can use bacteria, yeast, or plants, and grow them in the presence of carbon-13 glucose in a bioreactor. Then we can get these microorganisms and proceed for metabolite extraction and finally generate metabolite extracts for polar metabolites or lipids with above 99% of labeling efficiency. Once we have these extracts, we have the lipid and polar extracts from the carbon-13, but also from the carbon-12 microorganisms to compare that are generated in the same way, but they are fed by carbon-12 glucose, normal glucose, instead of carbon-13 glucose. We proceed to the generation of MSMS data. So first, we analyze these extracts by different analytical platforms. Then we process the data with XCMS for peak detection, alignment, and integration. We use the output data by XCMS as input for X13CMS that is able to sort metabolite by isotopologs. And I'll show you one example here. What this software does is taking one metabolite or one feature in the unlabeled data and taking all the co-eluting peaks of similar intensity in the carbon-13 labeled spectra, whose mass difference with the unlabeled is represented by an integer number of the mass difference between the carbon-12 and the carbon-13 isotopes. And finally, once we have this group of isotopologues, we proceed for the fragmentation and the analysis of the MSMS spectra. So what we have at the end of the day is pairs of spectra like this, and we generated hundreds of these pairs of spectra. In the upper part, we have the unlabeled metabolite parent mass, and in the lower part we have the carbon-13 labeled metabolite parent mass. That, of course, is shifted in mass due to the presence of carbon-13. Then we fragment the carbon-12 metabolite, and we get these fragments, and we do the same for the carbon-13 metabolite, and we get the same fragments, but with a different M/C ratio due to the presence of carbon-13. So knowing this difference between the mass of carbon-12 and carbon-13 isotopes, we can know the total number of carbon atoms in that molecule as well as the number of carbon atoms in all its fragments. And we can integrate this information with the methods that Rafa showed before to gain insight about structural properties of molecules, as I'll show you in the next section. So now I'll show you 3 examples of how to use this for the identification of unknown metabolites. So maybe you are wondering, okay, what's the way to proceed here? You generate these pairs of unlabeled versus labeled MSMS data, but what about if I have an unknown in my data or in my samples and I want to use that information to identify my unknown? Okay, so let's suppose that we have an unknown here with this mass and this is its MSMS spectra. Okay, so the first thing that we should do here is use any of the other classic methods to try to identify this compound. Like, of course, a spectral database search, that is the easiest one, and if that doesn't work, a neutral search or similarity search or bibliography or whatever. If you are able to identify that compound using this method, that's all. You are done. You got it. But the problem is in metabolomics, I would say that at least in 50% of the cases, we cannot identify our unknowns only using this information. So in that case, we can take a look to our data and try to find the same peak in our unlabeled data. Of course, should accomplish these 2 conditions. The first one is that retention time is similar under the same analytical conditions and the MSMS of the unlabeled is the same. If we find it, like this case, retention time is similar, the MSMS is similar, of course the intensities are not exactly the same, but yeah, it's that one, we can proceed to use the information provided by the number of carbons to identify the metabolite. And if we are lucky, we can identify it. Okay, so this first example is very simple. We have a metabolite with this mass of 482.32. We search for possible metabolites there, and we get these 4 possibilities. So first information we have is the total number of carbons of our metabolite. In this case, 23 carbons. So we readily rule out the last 2 possibilities, and we keep only these 2 lysolipids. Next information provided is the number of carbons of the fragments. And here we observe that in a molecule with a total of 23 carbons, we have fragments of 21 and 2 carbons. So probably the molecule is being fragmented, producing one fragment with 21 carbons and another with 2 carbons. So now just taking a look to these 2 structures, which of them would you say that is more likely to be fragmented, producing one fragment of 21 carbons and one fragment with 2 carbons, also attending to the fragmentation rules that Rafa explained before? Okay, so just let's do it. Okay, so these molecules can be fragmented. For instance, here between this carbon-oxygen bond, but in this case, this would produce a fragment with 15 carbons, and this would produce a fragment with 18 carbons. So that doesn't make sense with our spectra. But these molecules can also be fragmented here. So in this case, this would produce a fragment with 18 carbons here and 5 carbons here, but this would produce a molecule with 21 carbons here and 2 carbons here. So just taking a look to the structures, I would say that our unknown here is the lower. That actually was confirmed at that lyso-PE species. The second one is my favorite example, because in this case we found this feature in one of our projects that was highly dysregulated, as you can observe there, but we couldn't identify it at the beginning, and the project was in standby at that moment, waiting for the identification of the compound, and thanks that we could identify it, we could continue with some follow-up experiments. So we have this feature, we search for that mass, and we get all of these possibilities. Uridine, pseudouridine, molecules with these formulas, and many others. Okay, as always, we fragment that feature, and we get this MSMS spectra. But this time, unfortunately, we couldn't find any hit with Medlin or other spectral database. So we searched for that spectra in our isotopic data, and we found it. Okay, so let's start with the analysis. Here we have a molecule with 9 carbons, so we forget about those 3 possibilities. We also forget about uridine, because uridine MSMS is in Medlin, and trust me, it's not this one. And we only keep pseudouridine and other metabolites, some of them with 9 carbons as well, right? Okay, so I think here the most straightforward way to proceed is, okay, let's suppose that is the most likely option, in this case pseudouridine, and let's try to use the information provided by the number of carbons of each fragment to confirm that the structure of pseudouridine is coherent with the fragments that we are observing here. So okay, that's the structure of pseudouridine, and let's take a look to this fragment of 153, and we observe that this fragment has 6 carbons. And let's count, that's easy, 1, 2, 3, 4, 5, 6. If we fragment the molecule here, the mass that we get is exactly 153.0302. That makes sense with the structure of pseudouridine. Okay, then let's take a look to this other fragment. This fragment has 7 carbons, so maybe it's this one, but fragmented here instead of here. If we do that, the rest of the molecule has a mass of 183.04, so also makes sense with the structure of pseudouridine. And finally, if we consider this fragment has 5 carbons, so if we count 1, 2, 3, 4, and 5, and we fragment the molecule here, we also get that this mass is 140.0338. So all makes sense with the structure of pseudouridine, but since this project was important for us, we bought the standard, we ran it in the same conditions, and we confirmed that that unknown that we had was pseudouridine. The final example is a little bit more complex, because in this case, at least in the other 2 examples, when we searched for the mass, we had some putative metabolites, so it's like a starting point to ruling out some of them and trying to get an ID for the metabolite. But in this case, we searched this mass with this error of 10 ppm, and we couldn't find any hit in Medlin and PubChem, that are databases with millions of structures. And we only observed 3 fragments here, and actually one of them is the water loss, so we don't have much information here. So this is a real challenge. How can we identify this compound? But okay, let's start from the information we have. I mean, we have the M/C ratio, so at least we could get the list of putative formulas within this error of 10 ppm. In this case, we had 42 molecular formulas, not 42 possible metabolites, 42 molecular formulas, with each formula representing probably several metabolites. So probably we are talking about thousands of possible structures here. But is there any mean by which we can reduce this number of molecular formulas? Of course, because we know the total number of carbons of our metabolite, 30. So let's try to reduce this and say, okay, show me of these 42 formulas, only those containing 30 carbons. And we got only 2. Okay, we are a little bit closer, but still far away from the identification. Other information that we can use is this fragment. This is a very high fragment, so we can apply the fragment similarity search, and the only result was lycopene. So the only metabolite with MSMS in Medlin. that shows this fragment is lycopene. And actually, the prediction for that fragment is this formula, C35H47. So it doesn't make any sense here because we have a molecule with 30 carbons, so it's hard to have a fragment with 35 carbons, and actually we know that this fragment has 22 carbons. So I don't think that there's any similarity between lycopene structure and our unknown, so we forget about that. So maybe if this is not a fragment, it's a neutral loss from the parent mass. Okay, let's calculate that neutral loss and let's search with our neutral loss search for structures that can be represented by that neutral loss. And we got 10 structures here. That still is a lot. But can we reduce that number? Of course, because if we observe the neutral loss in the isotopic data, it's not 141, it's 143. So that neutral loss contains 2 carbons. So if we introduce that, the only possible structure with that neutral loss is the phosphatidyl ethanolamine. But not only that, because we see a phosphorus atom here. And from all these formulas, the only one with a phosphorus atom is this one. So we keep this one and we forget about the other. So starting from nothing, at least now we have, or we think we have, part of the molecule and the molecular formula. It's not bad. So this is a summary. We have a molecule with 30 carbon, with that formula, with the phosphatidyl ethanolamine group, and with the rest of molecule being this one. So now we hypothesize is this metabolite with this structure. Okay, this is a diacyl PE phospholipid, because these are very well-known molecules. But this would be weird, because these molecules have been widely described, so why we are not having any hit when we search for that mass? In Medlin, in PubChem, or not even in lipid maps, that is like more specialized for lipids. But it could be. But not only that, because if we count the number of oxygens here in a diacyl PE phospholipid, we have 1, 2, 3, 4, 5, 6, 7, and 8. And we have a molecule with 9 oxygen atoms. So we are missing one more oxygen. But that's okay. I mean, these are fatty acids, can be oxidized, especially if they are unsaturated. So let's suppose that we have a PE phospholipid with unoxidized fatty acid, being the total number of carbons, is the rest of the molecule, 25, counting the 2 fatty acid chains of the molecule. So we are a little bit closer, but still far away. But once that we are here, why not going a little bit farther? And we searched the bibliography, and we found that compounds like this that we are hypothesizing have been found in bronchoalveolar lavage. And in the same biological system, we found the discovery of this phospholipid that actually has not the P head group, it's a PC. But if you take a look to the fatty acid composition, it's composed by palmitic acid, so 16 carbons, nonanoic acid, so 9 carbons, 16 plus 9 equals 25, the total number of carbons that we are missing. And it's also oxidized, so makes sense with the type of structure that we are looking for. Okay, so let's propose the next. Let's draw this molecule, but with the P head group instead of the PC. We did it, and we found that had the formula that we were looking for and the exact mass. Doesn't mean that this is the molecule that we are looking for. It's not possible to say that 100% sure, because we should synthesize it and run it at the same analytical conditions, check the retention time is the same, maybe running in negative ion mode, and so on, and many other things. But at least we were able to come up with one particular structure starting from 0 putative metabolites. So finally, as a summary of all of this part, I've showed you 3 examples about how to use this information provided by the carbon-30 label metabolites to identify compounds. But now we are currently in the process of adding new layers of information to this. For instance, why not using nitrogen-15 label metabolites? Because in that case, we could have the total number of nitrogens and the number of nitrogens of each fragments, right? And why not also use sulfur 34 label metabolites? And we could have the total number of sulfur and the number of sulfurs of each fragments. And in that case, I think that adding these 2 new layers of information would help in the identification of, for instance, amino acid derivatives, of nucleotides, or sulfur-containing compounds. But the take-home message here is that generating this data in an untargeted way, we are generating hundreds, but not thousands of pairs of spectra. We are incorporating all that information to the classic methods for the identification of compounds to accomplish the identification of unknown metabolites. That nowadays is still the most limiting step in the metabolomics workflow. So the conclusions are that the endogenous isotopic distribution of a feature may help with its annotation and identification, and that a precious endogenous versus isotope-labeled MSMS data can be generated from extracts of isotope-labeled microorganisms. And this data can be used to help with the identification of metabolites that lack of MSMS data in databases, or even to discover new metabolites. So thank you very much for your attention, and I'll be very happy to answer your questions.
What gives rise to the mass defect?
What's up?
What physically gives rise to the mass defect?
You mean from the physics point of view?
Yeah, like why do you see?
I think it's because the bond energy in the nucleus. So in some atoms, when the energy is used as a mass effect, it's the formula of energy and mass, the relationship between energy and mass. So I think that some mass is lost due to the energy used for the bond in the nucleus. And I think actually that's the reason, because the atoms with a high number, like phosphorus and sulfur, have a negative mass effect, because they have more neutrons and more protons and these kind of things. I think it's that, but I'm not sure.
Sorry to ask you a physics question. Thank you. No, that makes sense.
So you have a couple of questions from the online people. Generally, I'm going to try and summarize this. We were kind of chatting back and forth on it, but is it possible to do a SILAC-type-like experiment and pool your metabolites and then get the quantification from them as well while doing this identification?
Doing the identification. Yeah, and actually this approach was initially envisioned for that, not for SILAC, but for quantitation. We add the isotope label extracts, and we have a lot of internal standards in our samples, so we can quantify a lot of metabolites even when we are doing an untargeted analysis. So we don't even need to make MSMS or anything, or triple quad. So that's the first approach by this approach was used. So maybe that's a good idea. I mean, adding the extracts and being used not only for identification, but also for quantitation of samples. So yeah, it makes totally sense.
Do we have any other questions from the audience? All right. Well, in which case, please join me in thanking all of our speakers today. And again, thank you to everyone here and to everyone online. Again, just to let everyone know, if you want to see any of the presentations, they will be available on YouTube. For those of you who are not there already, just go on to YouTube, and if you type in XCMS Online or XCMS Institute, it should come up, and you'll see this page. Thanks.